2, 1. So, everyone, thank you all for coming to the final episode of this year's Virtual Dynamic Walking 2021. Thank you all for coming. We're so glad to have you. We got a great speaker lineup that I want to get right to. Just a quick few points I would love to get to first. One is I'm Christian Ubicki. I'm an assistant professor of mechanical engineering at the FAMU FSU College of Engineering, and I'm pleased to co-organize this conference with Greg Sawicki at Georgia Tech Mechanical Engineering. And we couldn't have done this without all the great help from our lab members and co-organizers here: Jennifer Liesma, Lindsay Trejo, Dr. Owen Beck, Tienza Wang, and Jacob Hackett from Greg and my labs, respectively. So thank you all. Silent virtual applause to all of you for making this whole conference work. Thank you very much. And so the theme of this conference, this third episode, is about tasks and objectives. Basically, sort of the why are we doing what we're doing part of locomotion and how we make that happen. Sort of the big. So that's the idea of this conference, and that's the theme. And you can find on dynamicwalking.2021.org. You can find our full schedule for today. You can see this flyer and everything associated with all the talks. And you can find us on YouTube live right now. Hello, YouTube. It's great to have you. So, without further ado, I'd like to turn over the reins to Dr. Bobby Gregg, who is an associate professor in the electrical engineering department at the University of Michigan and the associate director of robotics. Is that correct?
That's right.
Fantastic. So he's going to be moderating our first session today, which is going to be about robotics. So without further ado, Bobby, if you could take it away.
All right, my pleasure. Thanks, Christian. So I'm going to have the great honor of first introducing Kevin Green, who is a PhD candidate at Oregon State University, is going to be talking about physics first reinforcement learning for the Cassie robot. So take it away, Kevin.
All right, everything's showing good?
Yep.
Awesome. So thanks to Christian, thanks to Bobby. So we're talking about our physics first reinforcement learning for Cassie here. And so this is really a work from a bunch of people in my lab that Jonathan Hurst leads here at Oregon State. And particularly, this talk's going to go into detail on more specifically than just physics first reinforcement learning. We're really going to get into this observation that we found that agile gates, they trade off robustness with performance based on their uncertainty, and particularly the uncertainty about their environment. And so this work is really based off of a number of papers over the past year. And I really want to shout out to Jonah and Yesh, two researchers from our group who did some really amazing work that will make up the first half of this talk. So a bit of a background, we're not going to go too deep into reinforcement learning theory, but to understand some of what's going on, we really need to get a bit of this internal model. So when we talk about reinforcement learning, we generally think of it in this actor environment back and forth, where the actor is this control policy, which will apply an action. In this case, we almost always use motor PD targets. It will apply that to the environment, which will move forward some amount of time, and this environment can either be simulation and training or the real world for when you're actually using the controllers. It will move forward, we'll run a state observer, which is actually part of the environment in our model, which gives us back a state observation that our control policy can then act on. And then the idea is that by creating a control policy that maximizes some reward, we can create a really functional control policy that works great in the real world. And so part of this is that we have an optimization algorithm, which takes a reward, which is built off a reward function that we design. And so this is great from a learning standpoint, but I'm much more of a mechanical engineer. I think of myself more as a controls engineer. So the question is, how can we engineer the system to create the most functional, capable controller that we can? And the first thing that we can control is really this reward function, because that's telling the robot, the simulation, and the learning algorithm, what do we want to happen? Because what the optimizer is doing is it's trying to maximize the expected reward, so the average reward that you will see as you execute your actions, over, and this is an important part that I think isn't emphasized as much, over the distribution of environments and experiences that you see. And so one of the things that we do, because no simulation is exactly accurate, it's not perfect, there are just a lot of them are useful, we will randomize a lot of parameters of it. And so in my mind, I separate this into dynamics randomization and environment randomization. we talk about dynamics randomization, we're talking about inertia, damping, mass of the robot, maybe even the ground contact models, things like that are intrinsic to the robot that the model is wrong. But this should cover the distribution of what the real world is. Then there's also environment randomization, which is saying, what is the set of environments that we want this controller to be successful at? And they're kind of the same thing, but I think separating them is useful in terms of an approach. So we're looking first at this reward function. And so one of our goals is to create an unbiased reward. And what I mean by biased, so up until about a year ago, all of the work that we've done, and honestly, most of the work I think I've seen, at least for Cassie reinforcement learning from different labs, we use reference motions, whether they come from just an animated motion, an optimizer, hybrid zero dynamics, something like that. You have a reference motion in terms of your overall robot trajectory. And then you create a reward function, which is to match that nominally as you locomote and move around the world. Obviously you can't do it exactly in all situations, but this really creates a dense reward that is really informative, and you'll end up getting reliable, predictable gates out of your learning algorithms. But in some ways, it limits the space of it. You're over-specifying the motion. Maybe that leg swing profile that you animated or came from a different controller isn't actually that great. Maybe there's some real problems with that dynamically. So we'd like to create a more objective reward function. And so one thing that Jonah and Yesh came up with in their ICRA paper is a way of creating a reward function that only specifies the gate really in terms of the contact sequence. So this is a chart that probably we're all pretty familiar with here. Here is, so this would be an example of a walking gate. So you can see as percentage of gate cycle, you have an overlap between left and right contact, so you have a nice walking gate there. So we turn this into a reward function by turning it into really an expectation of if your foot is in contact with the ground. So here, when the plots are high, that means that you expect to be in contact. When they're low, you expect to be in your swing phase. And how we turn this into a reward from here is then we just say, if you expect to be in contact with the ground, we're going to penalize the left foot velocity. And if you expect to be swinging, we're going to penalize applying forces with that foot. And what this does is by doing it as a penalty, you're not specifying how the foot should move when it's in swing. You're just saying you're allowed to move it now, where other times you're not allowed to move it. And this actually works amazingly well at creating the whole spectrum of bipedal gates. So here at the top, you can see the periodic functions, and you can shift them, their offsets, their lengths, how big everything is. So we get from a walking to a kind of gallop, and a gallop with a much longer aerial phase. You can go from standing, which is zero velocity, and you're never allowed to have velocity in your foot, to a walking gait and back. And so one thing about all these controllers are trained with dynamics randomization. So we randomized the parameters of Cassie, but we didn't randomize the ground. So they have only seen flat ground in simulation. And so it's somewhat surprising that it's able to take that curve so well, and we were really excited about a lot of this. And so we're wondering, okay, these are working really well. How far can we push this? And so what we did is we took these controllers and we ran a 5K with them. So we took it out to our intramural turf field here at Oregon State, and we ran a 5K in 44 minutes with no human intervention, no falls. And this is, once again, no terrain randomization, which works pretty well because this is about as perfect of a surface as you can get, right? Engineered to be consistent and flat. And so we completed in 44 minutes, which turns into an average speed of 1.9 meters per second. Which is, for the runners out there, a 14-minute mile pace, which for a human, not the greatest, but for a legged robot, definitely pushing some of the limits of what we can do. You see Jonah has to jog every now and again to catch back up. I believe the hot lap was at 2.15 meters per second, which is actually this lap. That was really exciting. But then again, this is a cool demo, right? It's efficient. It can run at a pretty good speed, but how useful is this, right? This is a perfect surface with a human guiding it. We really want to be useful in the real world, where there's curbs, where there's staircases, where there's things like that. So what situations is this controller not good enough? And what we found is when you get to pretty extreme environments, like a flight of stairs, this has some trouble. So it can take like one of these step downs But when you get a whole sequence of them, it kind of falls forward and it can't catch itself because it's used to flat ground. It changes the foot placement based on the assumption the ground will be flat in the future. And so how can we go about solving this problem? As engineers and roboticists, the approach is, okay, let's grab a RealSense camera, let's set up a SLAM algorithm, let's model it, and let's feed that model into our controller somehow. But is that really necessary? How much of this is that, stairs are just too hard to do? And how much of it's actually that it just hasn't had enough experience on this type of environment? So what we did is we took that exact same reward function, where it's mainly based off of the contact sequence, no real trajectories. So it doesn't tell what the swing leg is, doesn't tell it how the body should move. And we randomize the environments. So we give it flights of stairs, mainly in simulation, where we vary the dimensions of them, we vary the count, and then the ground slope leading up, the distance to it, this landing width, because we always give it this sort of plateau. And we just train the exact same problem, but instead of flat ground, you have these things of stairs. And it turns out it works really well. We're able to go up and down stairs. You spin around here and come back down. And so part of things to keep in mind. So one of the cool things that, to me at least, is seeing that it works well even when it doesn't get 1 foot per stair. That's obviously ideal, but it can slip off of them, skip steps. I think coming down here is a pretty interesting one in particular. And it's best if you can get 1 per step. So there's kind of an interplay here that is in the surface. So Jonah is off screen with the controller, giving it a speed to go up and down the stairs. And it's most reliable if he gets the speed right, in that if he can line it up so that you get 1 step per stair, so you can match the speed and the step frequency and the distance between stairs. But you don't need to. It's robust. It can handle missing them, slipping, and catching itself. And one other observation we kind of saw is that it really shoots these feet down, right? It's, if I had audio on, it's pretty stompy. You can go check out, we have some YouTube videos up of most of these ones I'm showing here. It's a pretty loud walking gait. And so these work really well. So we took it off and we did a 5K through campus. So this one took 53 minutes this time, slightly longer. The other thing is we actually fell twice. The first fall was we twisted a little bit, or what it was. There's a combination of the policy failing and the operator exact back and forth. You could say both of them are kind of responsible because the policy should handle it and the operator maybe should know better. We were making a turn at a pretty high speed on a crowned road and really started to struggle. And so the cool thing about this is a stair policy. This was trained. It expects to run into a flight of stairs at all times, but it ends up with a pretty efficient, pretty reliable gate that works well for this. The second fall also is when the computer overheated. In the Oregon sun, which can be surprisingly intense, we ended up overheating the computer and it shut down. But we just picked the robot back up, got the controller running again, and just kept going. So maybe not as true of one, but probably a more exciting one in terms of the dynamics and the control, in my opinion. And so this is really cool. We got these controllers to work, but why did they work? What's the difference between them? Is this controller actually have a different gate, or did it just learn more reactions to a wider space of disturbances? So we took a look into simulation to understand what they're trying to do. And I think the most interesting one to look at is how is it swinging the foot? Because to me, that's one of the most important parts of dealing with these ground height disturbances, because this is going to impact a lot of what your under actuated dynamics will do over the course of the next step. And so the first obvious thing we see is that the peak of the leg swing is higher, which makes sense. You need to actually be able to step up onto them. You can't stub your toe and fall forward, which makes sense. But the other more interesting thing I see here is the very steep descent of the stair policy swing foot. And this is kind of interesting. A little more useful, though, maybe, is to look at it from the framework or from the viewpoint of leg swing retraction. So if you look at it from that view, so what we're looking at now is the leg angle as it approaches a drop step compared to the body of the robot. And we can see a way larger variation in that leg angle for the stair policy. So as a much stronger leg retraction, it pulls the leg farther forward beforehand, and pulls it backwards faster. And, because it wouldn't be dynamic walking if we didn't bring it up, this is the sort of thing that we see from Monica Daly's famous tissue paper experiment. So we can see that we have a similar strategy here in terms of that leg swing retraction between nominal ground and drop step. And we see vastly different touchdown angles and leg swing retraction rates. But I think these guinea fowl are moving much, much faster compared to leg length if you go through the non-dimensionalization. So I'm not too worried of that difference there. But we see a pretty interesting change in that. And one other interesting thing about these that we came to is that we end up using significantly more energy for one of these stair controllers, even when we measure on flat ground. So if we calculate our cost of transport using a simulated motor energy, what we see is that the stair policy uses between 15 and 20% more energy just for nominal locomotion, which you would somewhat expect, right? If you don't know the ground in front of you, you're going to be a little more conservative. You're not going to be as streamlined and efficient, perhaps. But what does it take to get that energy back? And it turns out all you actually need is one bit of information. You don't need a perfect model of it. You don't need a great model. If you just know if there are stairs in front of you and you feed that in, so within 1 meter of my robot, is there a flight of stairs? You can basically get almost all of that efficiency back, at least within standard deviation. And I think some really exciting stuff and some thoughts I'd like to conclude with and maybe get into discussion here. So in reinforcement learning, one of the key advantages to me is that you can control a distribution of environments and you can optimize across a distribution. You can get really cool sim-to-real transfer with locomotion-specific rewards. Treating it like a generic problem isn't successful to the real world, in my opinion. Learn controllers, you can actually get some biologically recognizable strategies out of them, which is pretty exciting. And here's a little bit more. So dynamic locomotion balance shouldn't rely on accurate perception. You don't absolutely need it. It can be helpful and it should be able to raise your success probability. But if your camera goes dead, you should be able to stay upright. All right. So I'd like to thank Advisor Jonathan Hurst and Professor Alan Fern from our electrical engineering department. The rest of my lab, particularly Jonah, Yesh, Halle, and Jeremy for all the work with the 5K. And I think we should take it to questions and discussion.
All right. Thank you, Kevin. Very nice talk. Great videos. Lots of fun. Who's got a question? All right. Jim has a question. The stair policy appears to employ gaits with more stance knee flexion. Is that the dominant factor in the larger energy consumption?
Let me see. Are you talking about in terms of like it's a more squatted gait, or it actually dips lower during it? I'm not sure. I'm not super familiar.
No, it's a more squatted gait in my observation. When you're walking on flat ground, it just, in the original videos, it just looks like your knee is much straighter with the previous controller. And when you switch to the stair controller on flat ground, you've got a much more bent knee, which would seem to indicate, larger energy consumption.
Yeah, I think that's definitely. I would definitely believe that's part of it. It makes sense also because I think one of the parts of the strategy of what you're doing with the swing leg is you want to be able to compress the uncertainty in terms of your time of contact, right? Because the sooner, the smaller the deviation with a step up or down or flat, then the better it is. And I think you see particularly here that we're getting close to some of our extension limits on the larger step downs. So we didn't specify the body height, we didn't reward it. So that's an emergent thing, the squat height it chooses. And I definitely think that's probably a part of it, which makes a lot of sense. Great observation. Thank you.
All right. So we have a question from YouTube. Between the flat ground versus staircase controller, what parameters in the controller changed in addition to spatiotemporal parameters?
So in the controller, right, all the parameters in some way change. So we're using a neural network, which is re-optimized completely from scratch. Mm-hmm. The reward functions are exactly identical. It's trying to optimize the exact same performance measure in both. So in that way, none of the parameters changed. And the other way, the distribution of environments changed completely. So that's all we did, is that instead of seeing the world as a flat, infinite flat plane, it saw it as, it's in a gymnasium with the lights off with flights of stairs all over it. And that's its model of the world.
Mm-hmm. All right, so another question from YouTube. For action output, do you think it's really helpful to include proportional derivative gains as your colleague did in ICRA 21?
Yeah. I'm not convinced either way. I don't think we know. It makes a lot of sense that we should, because you think how you react in the timescale. So one of the things about these neural networks is that they're pretty slow. So from a controls perspective, these are ludicrously slow. They're running at, I think, 40 or 50 hertz, depending on which controller we're showing, because we varied around a little, compared to, hundreds or thousands that you do in normal control methods. And so in the time in between one of these neural network updates, how your robot behaves is entirely based on the feed forward command and then that PD. And so I think that matters quite a bit. I don't know. We haven't seen huge gains, and adding the extra dimensions to the output space has not shown dramatic gains. So I'm not sure whether we're missing something or just we're not great at solving the problem yet.
Okay. So I think that'll have to do it for our questions. We should probably move on to the next speaker. So thank you so much, Kevin. I really appreciate the talk and the question and answers.
Thank you, everyone.
All right, so time for our second speaker. So we have Dr. Kwan Nguyen speaking about the development of adaptive intelligence for dynamic legged robots. And Dr. Nguyen is from the University of Southern California. So take it away.
Okay, thanks, Bobby. Should I start sharing my screen now, Kristen?
Go for it.
Go right ahead. You should be, hopefully you're able to.
Your microphone's a little scratchy though.
Okay. Wait.
If you speak up, I think you'll be okay.
Okay. Is this fine now? How about the presenter?
It's possible you changed your microphone settings from when we tested earlier. Is that possible?
Yeah, it sounds like it's muffled, like maybe it's your laptop mic or something.
I'm not quite sure if I need to change anything, but maybe let me try.
Yeah, if
Is
you
it
go to
okay
your,
now? Can you hear me okay?
yeah.
It's the same microphone. We can hear you though. So yeah, if you speak loudly and clearly, you'll be okay.
Okay, that's good. Thank you. Okay, so thanks, Bobby, for the introduction, and thanks, Kelvin, for the great presentation. Also, thanks, Kelvin, for having some nice review of deep reinforcement learning, and it's very helpful for my thoughts as well. All right, so it's my great pleasure for me to give a talk again at the Dynamic Walking Conference. I'm very happy to be back at the conference, even if it's online this time. But I hope to see you all in person again soon in the upcoming years. So in this talk today, I would like to add some thoughts to Kelvin's presentation on learning and control of lateral robots. So in our lab, we are working on adaptive control and reinforcement learning for dynamic lateral robots. So today I will present some of our recent results we have in the lab regarding these topics. And then I would like to share some thoughts on outgoing and future research towards the development of adaptive intelligence for dynamic lateral robots. So to give you a better picture of the talk today, I would like to give a brief highlight or overview of my research. So I have been always motivated by the dream of having robots that are capable enough to have humans in a dangerous jobs such as disaster response or firefighting. So I know this is nothing new, but I think this also because the problem is very challenging and we are still not quite close to discover that. So, I also believe that adaptive locomotion and manipulation are also some of the key challenges for some applications. So toward achieving this goal, I have been working on adaptive bipedal locomotion that can adapt to extreme terrain, such as stepping stones, or adapt to model uncertainty, for example, walking while carrying a heavy load. So my prior works also include trajectory optimization for quadruped robot thumping and force control for quadruped robots navigating rock terrain. And in the last 2 years, George USC, we have continued to work on this direction and gain some new results, and I'm excited to share them with you today. And the ultimate goal of my research in the near future is also to develop adaptive intelligence for dynamic humanoid robots. So I hope to give some thoughts about this direction at the end of the talk and hope to get some feedback from you all about this too. Okay. So, all right. Firstly, I'm going to present briefly my prior work on adaptive control for bipedal robots. I actually present this work with Kausho at the Dynamic Walking Conference a while ago. So because it's a prior work, so let me just go over it very quickly so that we can have more time for some new results. Okay, so in this simulation, we focus on the application of dynamic walking of bipedal robots while carrying an unknown and time-varying load. So here the unknown load is changed randomly from 0 to 30 kilograms for every walking step. And for comparison, the robot weight is only about 32 kilograms in this simulation. And as you can see, the value of loads, the load share is changed for every walking step, but this is unknown to the controller and it needs to adapt to this unknown variable. So let me explain the approach very quickly. So in this diagram for our proposed adaptive control, we firstly introduce a reference model or the state predictor that mimics the nominal system with our model uncertainty. So if there's a model uncertainty, for example, if the robot needs to carry an unknown load here, we will have the difference between the real system and the reference model here. Okay. So then in this adaptive control framework, the adaptation law will compare the difference between the real system and the reference model to estimate model uncertainty. So that is the basic principle for our prior work on adaptive control for bipedal robots. However, this framework is based on trajectory tracking, where the trajectory is generated by using hybrid zero dynamics. So next, I will talk about our recent work on adaptive force-based control for legged robots. So to clarify, force control here means we design the controller based on the control input of ground reaction force. Okay, so the motivation for this work is that we have observed many advantages of force-based control using either QP or MPC controller for quadruped robots. So for example, this type of controller is kind of robust to rough terrain. It can also enforce sharp impact and friction constraints in the controller. And we can also use almost the same controller for different gates and velocity commands as well. So to illustrate this, I would like to show here a video of the MIT Cheetah robot climbing stair blindly using MPC controller. So it means that in this case, without having any knowledge of the terrain or stair, but the force-based control is still very robust to the unknown terrain. So, however, with the current adaptive control framework and also our prior work on adaptive control for bipedal robots that I have just presented, they are based on trajectory tracking. So it also means that for legged locomotion, you would need different trajectories for different motions. Okay. So therefore, we want to develop an adaptive control framework that can leverage the advantages of the force-based control framework that I have just mentioned before. So let me explain the general idea of force-based QP controller. So in this method, we normally use a simplified rigid body dynamics of the robot, and it can be written as this form. So where here F is the ground reaction force at forefeet of the robot, and the upper part in this equation is the dynamics of the center of mass position, and the lower part is the dynamics of the body orientation. Okay. So then the goal of this controller is that we want to drive the real dynamics to the desired dynamics. And to do that, we will formulate the controller using a quadratic program or a QP problem. And in the cost function, we will minimize the difference between the real dynamics and the desired dynamics. And as you can see, the way we design our controller here is much different from choice-free tracking. Therefore, in order to apply the adaptive control for this type controller, we would need to introduce a new control structure for this. Okay. And this is the structure that we have proposed in this work. So I'm not going to go into too details about this, but the general idea is still the same as model reference adaptive control, and more specifically L1 adaptive control in this case, where we kept design and adaptation based on the difference between the real system and the reference model, and we designed an adaptation law based on this difference. Okay. However, the key components here and then the new item here is that how we define the system state and control input so that we can convert the force control problem to something similar to a conventional tracking control problem. For example, we have some closed loop equation here that we convert the force control problem to something similar to this form. Okay. So with this proposed approach, we have achieved some nice results on quadruped robot. And this is the video to summarize our approach. So by the way, I'm very glad that this work was accepted and will be appear at the IROS conference this year. Okay, so this is the main result of this work. So as you see here, the non-adaptive control or the nominal QP controller failed with only 3 kilograms of load. But our adaptive control approach can let the robot walk stably with 6 kilograms of load. And the weight of the robot is only 12 kilograms. So it's 6 kilograms means 50% of the robot weight. Okay, and for the standing task, while the non-adaptive control cannot stand up with 6 kilograms, our adaptive control approach can let the robot standing up and keeping balance up to 11 kilograms. And in simulation, we can also test with some more challenging terrains and setup. Here we have an uneven slope, and the robot also needs to carry a load and get perturbed by some external force. Okay. So the other recent result that I want to present here that the work on robust high-speed running for quadruped robots using deep reinforcement learning. So the key idea that we implement in this work is that we want to improve the reliability and efficiency of deep reinforcement learning using the combination between deep reinforcement learning and impedance control. Okay. So the main reason behind this idea is because we believe that doing force control can have some advantages over joystick control, especially while considering to the adaptation to rough terrain. And another key reason is that foot position is very intuitive in locomotion. Therefore, we can easily estimate a reasonable range of the action space, which is very hard to do with the joystick space. And we can also better initialize the learning framework because we know what is the normal expected distribution of the foot position during locomotion. Therefore, we expect that this approach can have the learning framework to learn faster and more robust to model uncertainty, and then also rough terrain. And this is our result for this work. So we trained the robot to run, and as you see here, interestingly, with our approach, the robot learned by itself a very natural galloping gait, and is normally observed in animals in fast running. And in order to test the robustness of the approach, we also teach the robot to learn to run while carrying a heavy load up to 10 kilograms. And again, the robot, our robot is only 12 kilobytes. Okay. And this also some rough terrain testing for the learning policy. And we also transfer our learning framework to our gazebo simulation. We're still working hard on transferring this to the real robot hardware. So hopefully we can get some nice experimental results. Okay, so this is for this work. So that is some of our recent results related to these topics. I'm also excited to discuss some ongoing future work in this direction. So let me go back to this diagram and go over it quickly. So I have to present some work on adaptive control, adaptive force-based control, and deep reinforcement learning for quadruped robots. And we're also working on force-based control for bipedal robot, and I'm going to present it shortly. And in the future, we would like to extend our result from quadruped robot to bipedal robot as well. Okay, so towards this direction, we have been working on designing a mini humanoid robot, and we have finalized our results as seen in this figure. And we will use a modular A1 actuator from Unity Robotics for our design. So I think it's a very nice robot, and I'm excited to see what we can do with it. Okay, so I think I'm running out of time, so let me go over this work very quickly. So based on this robot model, we have also developed an MPC controller for this. So using this approach, we have the robot tracking different speed and performing different type of motion. We can also achieve high speed walking on rough terrain. Okay, and this is a simulation for high speed walking on rough terrain. And this is a slow motion video for this. And with the same controller, we always change the gate schedule, and it can achieve different kind of dynamic gates as well. And we're excited to complete the robot design part and implement this controller on the robot hardware. Okay. And lastly, so let me give some thought about the combination of adaptive control and deep reinforcement learning. So in my opinion, each of them have their own pros and cons, but they do share some similar principle and structure. Therefore, I believe that combining adaptive control and deep reinforcement learning could be a great tool for robotics in general. So to be more specific, adaptive control normally deal with low-level motor control, and it can achieve very fast adaptation. However, that is not enough for Lego robot. We need robots that can adapt with motion or behaviors in response to different terrain and scenarios. So this is a proposal idea that we are trying to do in the lab. We hope to do supervised learning to improve the adaptation law. And in the meantime, we hope to use a deep reinforcement learning to improve long-term adaptation for the adaptive control as well. Okay. So that is some of my thoughts on this. It could be wrong, but it could bring us some potential results as well. So I'm happy to get any feedback from you about this. All right, so that's all I have today. I'm sorry that I'm running out of time a little bit. So thank you for the attention, and I'm happy to answer any questions you may have.
All right, thank you, Kwan. So we have one question already. So with regard to the quadrupedal system, you showed a galloping gait, but do other gaits spontaneously arise in other circumstances, like slower speeds?
Okay, that's a good question. So in this specific simulation and application, we just try to focus on high-speed running. So that's appear that is show a galloping gait, but we haven't tested any kind of slow target yet. So maybe different gait could show up when we test with different kind of velocity or desired velocity for the locomotion. But in this specific kind of problem, we just try to set the reward function so the robot can run as fast as possible.
Okay. Other questions? So I guess I'll jump in with a question then. Have you ever experienced any problems with L1 adaptive control in terms of like robustness? Like, have you ever had any issues with adaptation going wild?
Yeah, so in general, it's obvious that there will be some trade-off between fast adaptation and robustness. If you have a very high gain in running high adaptation gain, it could cause some oscillation and instability. But I think with some reasonable range of gain for L1 adaptive control, and also the combination between the adaptation gain and the low pass filter gain, you can achieve pretty nice results. And when we tried it in experiment, it's actually very nice. We get some very nice results.
So it's a trade-off in the sense that you need to get it to adapt fast enough for the robot to not fall over, but not too fast that it also falls over.
Yeah. But
Okay.
but I mean that's if you turn the adaptation gain very aggressively in simulation, you may not observe instability. But
Yeah.
if you pick some reasonable gain, I think you can transfer the result from simulation to hardware very nicely.
Okay. So we should probably move on then to the final speaker of the session. So thank you, Dr. Nguyen. Appreciate the talk. So next up, we have my friend, Dr. Aaron Young from Georgia Institute of Technology, presenting on deep learning for predicting user and environment state in the context of control for robotic prostheses and exoskeletons. So Aaron, whenever you're ready, go ahead.
There we go. All right, thank you very much, Bobby. Okay, so thanks to the dynamic walking community for inviting me for the talk. I'm excited to share some of the stuff we've been doing in the EPIC lab. So I run the Exoskeleton Prosthetic Intelligence Control Lab at Georgia Tech. And for this talk, we'll kind of focus on some of the deep learning applications that we've been looking at in the context of control for robotic prostheses, exoskeletons. So a little bit of a change from bipeds to really thinking about control and where a human is in the loop. And so this is just a little bit of context for those who aren't familiar with our lab. We work primarily in wearable robotics and really specifically trying to understand the science of how control systems affect human biomechanics in clinical contexts and associated outcome measures, and especially for community ambulation. And so one of the main areas that we really think a lot about is in using devices to provide assistance across a wide variety of ambulation tasks. And this is one of the big aspects where patients really feel that there's a lot of value in terms of maybe wearing a robotic device over a more standard passive prosthesis, for example, and the ability to be able to remove power or add power strategically and change really the mode of operation of the device across a really wide range of contexts to allow for more easy community ambulation. But to do this, it requires fairly advanced control techniques. And so this is kind of a high level diagram of often how we'll break up the control, with kind of the high level control being at the top where state estimation occurs to understand kind of what the user intent is in the environmental state. From these set of states, typically some type of dynamics equations are implemented to transform from state to joint torque in a device. A very common form of that is an impedance controller, which we typically use in a lot of different contexts, though many other forms of control can exist at that mid-level control. And then at the low level, usually the commanded torque is servo to a realized torque with some sort of low-level control. But for this talk, we'll kind of focus primarily on the state estimation area of these wearables. So first, what are kind of the most important states to a human wearable robotic application? One of those is user intent. So trying to understand, for example, transitioning between different modes or changing speeds the environmental state, so whether it's rocky or flat or slope terrain, these are all potentially important things for controlling a wearable device. And then lastly, and we'll get to this later, is user physiological state. So what's going on under the skin? Muscles being fatigued, what are the underlying joint loads and torque? That may influence exactly what we want the wearable device to do. So I'll start kind of with some of our older work on user intent and build up from there. So user intent, one of the primary ways that we think about this is in terms of locomotion modes, such as transitioning between sitting, standing, walking, stairs, and ramps, very common terrain experienced in the community, with the general idea that we want these wearable devices to have an accurate way to seamlessly, naturally, and automatically transition between all of these different modes. And one of the classical ways that we've used to do this is through an idea of sensor fusion. So taking a lot of different sensors from the robotic device itself, as well as we can instrument the human with additional wearable sensors like IMUs, and then even taking some window of sort of their neurological signals. So usually from electromyography to get an idea of what the muscles are doing. And with all of this information, we can fuse it together to get a good inference of sort of the human intent. And so in some of our past research, we've looked at taking this into a standard kind of machine learning classifier, where it will choose, from all this different sensor information, it will create a likelihood of the different classes that they might be in. Usually a dynamic Bayesian network or something equivalent is used to incorporate time history into the classification decision. And then it will output the most likely locomotion mode. And this is some of the older research, but this can be used pretty effectively. So this is an example of using a machine learning system online, using both EMG signals as well as signals in the robotic leg. And he just kind of has to think about going up the stairs or down the ramp, and it's just classifying discretely these modes of ambulation, whether it's stairs or level walking or going down a ramp, pretty seamlessly to the user. And then with EMG, we can also kind of get the ability to control directly the knee or the ankle with the device. So I think overall, these machine learning systems in the combination of wearables offer a pretty, potentially a very powerful solution to enabling community ambulation, and certainly extends the capability of devices. But there's a number of problems or potential challenges to really making this clinically and real world realized. And so here's some of the main challenges that we've been looking to tackle. One is that this kind of standardized system that's been explored quite a bit in the literature is very discretized. So these sort of 6 locomotion modes aren't necessarily representative of real world ambulation. That is much more continuous environmental contexts. And a big challenge is, how do we generalize these AI systems more widely to what we actually face in the real world with wearables? And another challenge on generalization is, how do we extend these to novel users? So typically like the system that you just saw, it requires a lot of user-specific training data to get such a good system. And to really have it be clinically feasible, it needs to be able to generalize to novel users. And then lastly, kind of the inverse of this is, these systems require a lot of personalization. Usually we have to tune these with subject-specific parameters to get a really good, excellent control. And this isn't necessarily very clinically feasible when we want to be, these systems need to be personalized, but we need a systematic way of doing this that allows us to customize the controller to each individual's specific gait characteristics. And so these are some big challenges that we've been looking to tackle over the last few years in the Epic Lab. So one of our big areas and certainly a hot area in robotics in general, is in big data and artificial intelligence. And this is where we've invested a lot of time and resources, and specifically thinking about deep learning. So creating these algorithms to reason more like humans, to have a higher extended capability to hopefully generalize across a much wider set of tasks and users, and be able to also personalize the algorithm to somebody's gait, all with a deep learning system. And so to do this, what we've learned in the field, and what Apple and Google and others that have certainly taught us is it's all about the data. And really before investments in algorithms, the data is the most important key driver to create good AI systems. And so we've invested a lot of time in collecting robust data sets this is just demonstrating some of this with powered prostheses. We've also done this in able-bodied users as well as exoskeleton users, but collecting data across a wide variety of contexts. So showing experiments in which we were varying the stair height and collecting transitions between level and stairs, varying ramp incline angles, collecting transitions and different walking speeds using this kind of simulated terrain park where we can collect this multimodal, highly varied data to help simulate more of what might be experienced in the real world. And we have, so Jonathan Camargo, one of the PhD students in my group, just defended, created an open source data set that's available. This includes 22 able-bodied subjects. That includes motion capture, as well as full inverse dynamics, as well as wearable sensors. So EMG from all the major lower muscles, IMUs, electrogoniometers, FSRs, across different walking circuits that include turning, standing to walking, walking at lots of different speeds, going up different inclines, going up different stair heights, all of these different things where we can really look into how wearable sensors are able to predict a lot of these underlying environmental or user states. And so anybody interested, we have that now available for use. But what we've done, one of our first looks at this data was to create an environmental parameter regressor. And so the idea here is to add in the ability to create a more continuous identification of the environment. So this includes estimating, for example, that you're going up a ramp, but also that ramp is a 5-degree incline or a 10-degree incline. We're going up a stair and that stair is going to be 4 inches or 5 inches in height to allow for a more continuous scaling of robotic assistance across real-world parameters. And here are some of our results on this. This is kind of just classic classification, but in terms of the regression, we can typically estimate these ramp inclines on an unseen ramp or one that was not in the training data at about 1.3 degrees of error on the ramps, 1.3 centimeters on the stairs in terms of RMSE error. And this kind of just shows general tracking performance on the ramps and stairs. This is speed, so about 0.05 meters per second walking speed. So these machine learning algorithms usually do a pretty good job of being able to kind of estimate a continuous version of the environment. The big limitation that this study was a user-dependent analysis. So it required training data from the specific user, even though it's scaling across different environments very well. So what we also invested in is looking at independent models. So this is where we might train a machine learning system on 9 different subjects and then test on a novel withheld subject and try to create a fully independent model. Unfortunately, this increase, as you might expect, this does increase the error quite a bit. Usually we see about double the error in certain different tasks like locomotion mode recognition or walking speed estimation. So we're not super happy in terms of the ability of an independent model to fully work. I will say a caveat that it does work on certain things like slope inclines. It's much more accurate, but in certain areas, the fully independent system is maybe not as accurate as we would like it. And so what we've done to help address this is invested a lot in deep learning systems like a convolutional neural network that is adaptive. And so this is work that In-Sung Kang, also recently defended in my group, and Pratik Kunapalli have worked on that was published in TMRB, where we take a convolutional neural network and train it across a wide variety of different users. So this is a static layer. We learn the feature representation, a deep learned network across a wide number of different people, and then have a dense layer that adapts over time to a novel user, where we can backward estimate things such as the gait phase, so where you're at in the gait cycle, or the speed that somebody's walking at, which tend to be pretty easy to backwards estimate once you already have your data. And then we can adapt that in real time to be able to have a forward prediction of gait phase and speed. And so here's some data of what that looks like. You can see that the static user independent model, of course, isn't really changing over time, but the adaptive system in about 1 to 2 minutes tends to be able to learn the new representation of how somebody's walking and reduce the error to the user dependent rate. And so this potentially offers an opportunity to take these independent systems and online adapt it to personalize it to someone's gait. So this helps address some of the challenges potentially in both personalizing as well as adapting to novel users. But to take things one step forward in terms of control of what we've done with exoskeletons, we've started to invest a lot into looking at ways in which we can understand the underlying user physiology and incorporate that into the controller. And so 2 of the common control strategies in the field are, one is a biological torque controller, where basically you have different modes and you just simply play the average biological torque, or usually a percentage of that biological torque for a given mode in an exoskeleton. Another common strategy is using human in the loop optimization, where we take a metabolic cost value or some sort of outcome measure and use numerical optimization. But the disadvantage of that is it tends to be very slow policy convergence compared to a biological torque controller, which has sort of predefined control policy. One is generic. This is not optimal using biological torque. Human in the loop optimizer, of course, is very personalized and optimized to that gait, but you have to do it for every different mode. And so what we've done is kind of taken the idea of the biological torque controller, where it's a predefined policy, but replace that with a neural network that tries to estimate the underlying hip torque of someone as they're walking, and use this in real time to potentially command an exoskeleton. So the idea is that it's a predefined control policy that personalizes it to exactly what the person's trying to do. And we potentially generalize this across a wide range of tasks without having to sort of train it for lots of individual tasks. And so what our general hypothesis is that we can do a better job than just a generic biological torque in terms of being able to compute step-by-step responses to a human as they're walking. And so what we've done is taken a large data set again and tried to train wearable sensors and relate that to underlying joint torques or joint dynamics without force plates, essentially. So we use the gold standard inverse dynamics to compute the ground truth and labeling, and we create subject independent systems such that we're training, for example, on 15 subjects and then test on the withheld 16th subject. And this uses a deep neural network, a convolutional neural network, which I won't go into details on, but it's certainly available if people are interested. And we compute sort of the average error of this system compared to the gold standard baseline. And so here are some of our results. I'll show time series in a second. We can see that we're beating the baseline by quite a bit. So computing normalized torques much more accurately than just an average torque profile compared to the gold standard. This is kind of what this looks like in terms of time series data across ramps and stairs and level ground. So we're training an overall one single deep neural network that can generalize or compute biological torque of a human across all these different modes. And even when we leave out modes from the training set, so for example, leaving out different slopes or leaving out different stair heights, it still generalizes pretty well unless we're leaving out something that's in the extrapolation region and very far away, like this 18-degree slope incline, for example. And it even does a pretty good job of generalizing to transition data, even when the transitions are not within the training set. And so this potentially offers, I think, a pretty exciting method of extending control where we can estimate human physiology in real time. We've started implementing some of this in a hip exoskeleton where we're computing these biological torques in real time and using that to drive controller input. Since I think I'm running out of time, I'll be very quick. We've also looked at extending this beyond just kind of cyclical walking tasks to a large number of non-cyclic tasks. So in this case, we're expanding that open source data set. We've got 11 different cyclic tasks 20 different non-cyclic tasks. So these are like jumping, lifting, lunges, tug of war, squats, step ups, twister, lots of kind of, you can see different things that we've composed where we're measuring joint torques during all these different movements and trying to use a deep learner to predict these or extend these to generalize control across a wide range of tasks. And generally speaking, it seems to work pretty well. We've got pretty good RMSE errors. So I think in that 0.1 Newton meters per kilogram, that tends to have pretty good tracking performance. And in the leave one out or the red task, you can see generally, it doesn't do quite as well as if you train it with all the tasks in terms of generalization, but it's doing a pretty good job of generalizing to novel tasks. Here's some quick examples of various time series in which the deep learning system, again, with the red, so this is that same data, but now you can kind of see it in a number. Here's jumping back and forth, lunging. The red is kind of the time series that the deep learner is predicting. Green is the ground truth inverse dynamics. And across tasks, we at least are doing pretty well of being able to generalize to completely novel non-cyclic tasks. So we're kind of excited by this as being a potential way of really being able to generalize control to a lot wider range of tasks than kind of the standard classification approaches of a few years ago. Okay, with that, I'll finish my presentation. Thank you.
All right, thank you, Aaron. So I think we have time for one question. And so we have one from Andy. How much of the learning of intent is just measuring kinematics, and how much is real intent ahead of time without use of kinematic data from Stair's ramps?
Oh yeah, great question. I definitely didn't go into the details. So yeah, the intent is definitely picking up. So what we do is try to estimate the correct mode by heel contact onto that mode, so that essentially that swing phase over, as you're approaching a ramp or a stair is when it's trying to predict that mode. And so there are sort of subtle changes in kinematics that are occurring during that time. And so we are using data from the human in terms of them sort of changing a little bit of their stride parameters, and that's measured in both kinematics as well as sort of encoder data that can be picked up to be able to be correct at once you actually touch down on a stair or a ramp for the intent recognition. Hopefully that makes sense. So it's kind of a combination of both to some degree, but we are predicting it. It's not waiting until we're sort of on the mode. This is a forward prediction of state.
Well, like if you get to a ramp, by the time you put your foot on the ramp, then depending on how much kinematic data you have, it's kind of determined. It's not it's a kinematic, like if you have to do it, I guess to get full credit or to make it sound like it's intent, it has to be before the foot touches the ramp, right?
Well, it's only using data before it hits the ramp.
You're only using data before. Okay, that's my question.
Yeah. So like for example, at that heel contact, if you're transitioning there, usually I'll use about 300 milliseconds prior to that.
Okay, so it is a real prediction. It's not.
It is a real prediction. Yeah, the prosthesis, for example, has to be in the ramp mode at heel contact to have a smooth transition.
Good.
All right. So one more question. So what do you think is the minimal set of sensors for practical implementation purposes in long-term wearable device implementation?
Yeah, I guess it depends on what features, right, that you want the device to be able to have, and how broad the activities are. I mean, it's pretty, but I will say that it's pretty clear that there's a lot of information just with, ensuring that on your device there's an IMU on every moving segment, and the encoders provides a large percentage of this inference, or it seems like a lot can be done with sort of the standard sensors. And EMG certainly adds certain capabilities that you can't have without it, but I don't see it as being necessarily critical for a lot of the different things that I showed and that we might want in many of these wearables.
All right. Well, thanks, Aaron. And let's thank all the speakers one more time. So I guess now it's a coffee break. Is that right, Christian?
That's right. So thank you. First off, I also want to thank our esteemed moderator, Dr. Bobby Gregg. Thank you for keeping the trains running on time and keeping things going. So thank you to you. And thank you all of our speakers. So just a programming note, we will take a 10-minute break now. I have posted in the chat the link to the spatial chat, so you can go hang out there. We'll start at 2:45 Eastern time. We're pushing back our whole schedule 5 minutes to accommodate, and we'll see you in approximately 10 minutes.
Thanks, Christian.
All right. So everyone on YouTube, we'll reconvene in 10 minutes. We'll do a little bit of programming stuff here while we're waiting. We'll get our next speakers ready and look forward to seeing you soon as well. Hello, Needy.
Hey, Christian. Yeah, sorry about that. So it says host disable participant screen sharing.
Yeah, so while I'm going to now make you a co-host
Okay,
for
cool.
the next session. So give me a second here.
Hey, Bobby, thanks for doing this.
All right, so now, Needy, you should be.
Yeah.
You should be able to add here.
I'm
Should be a
still
co-host.
getting host disabled.
Okay, maybe I did not add you properly. Let me try this again. Make host. There you go. Let's try this again. You should now be available.
Okay, yeah.
Yeah, there you go. Thank you, everybody, for all your speakers. It's great to have you, all your input. Feel free to pop over in the spatial chat and relax and chat about your work. So I'll post that in the spatial chat.
Cool.
All right. So I see your preview screen there, Needy.
Awesome. Yeah, looks like it works.
Great. Do you want to check any videos out or anything to make sure that they play all right?
Sure. I mean, the videos are not super important, but
Okay. All right. Well, if you feel fine, then I feel fine.
okay.
Okay, Needy?
Yeah.
All right. I'll see you all soon. We'll reconvene in about 7 minutes. Just get ready to get started. Just one moment. Natalia, can you hear me all right?
Yes, perfect.
Fantastic. All right, just give people about a good 10, 15 seconds to migrate back on over, and we'll get started. All right. Okay, everybody, welcome back. It's great to have you all back here again. We will get more time and hopefully some great discussions going on in the spatial chat, which we will continue to have throughout the course of the remainder of this conference session. So it's my pleasure to introduce our next moderator today, Dr. Natalia Sanchez at the USC in the USC Division of Biokinesiology and Physical Therapy. She is a assistant professor of research and runs the Locomotor Control Lab. So it's really great to have you, and I'll get out of your way so you can take it from here.
Thank you so much, Christian, and thank you for the opportunity to moderate this very exciting session. Aaron's talk was actually a great segue into our session because we're now going to talk about the task objectives that shape human locomotion. Just as a reminder, feel free to enter your questions in the chat, or if you're feeling brave, use the raise hand feature and you can ask the question in person. And I am delighted to introduce our first speaker, Dr. Suravi Seema. She completed her PhD in biomedical physiology and kinesiology at Simon Fraser and is now a postdoctoral fellow in neuromechanics at Emory and Georgia Tech. Suravi, take it away.
Thanks, Natalia. Let me share my screen. Okay, yeah, so like Natalia mentioned, I'm currently a postdoctoral fellow at Emory, but I'm going to be talking about the work that I did during my PhD at Simon Fraser University. And again, like Natalia mentioned, I will segue into human controllers, which is our nervous system. When people start walking in new environments, they can adapt their gait to reduce their metabolic energetic cost. We've heard a bit about this in the previous dynamic walking episodes in the context of human exoskeleton interactions. This is an example of one such interaction. This was a study done by Jessica Sullinger using knee exoskeletons. Here, people walked on a treadmill at a constant speed while they wore these new exoskeletons, and she commanded knee joint torques as a function of their walking step frequency and was able to manipulate walking cost landscapes. So by cost landscapes, I refer to this relationship between metabolic energetic cost and a walking gait parameter, which in this case is step frequency. So over here, you're seeing three different cost landscapes. The gray curve is the original cost landscape, and you can see that people typically prefer to walk near the minimum of this curve. Now, Jessica Sullinger created two new cost landscapes given by these blue and red curves, and you can see that people now adapt their walking gait towards the minima in each of these curves. Now, here are two other systems where we observed similar behavior. In the center, we once again manipulated the walking cost landscape as a function of step frequency, but this time we manipulated using foot-aft forces applied to the hip of the walking user. And in the rightmost column, they manipulated the cost landscape as a function of step width using treadmill inclines. Now, this was a study led by Sabrina Abram. And the takeaway here is that these are all examples of people walking in different systems and adapting their gait to reduce their metabolic energetic cost. But the interesting thing is that people do not always spontaneously adapt. So what do I mean by this? If we focus on the bottom row are all time series data. So the x-axis is always time, but on the y-axis, we have either step frequency in the first two columns, or we have step width in the third column. And the bar just above the x-axis is when it turns green, it indicates that people are walking in the new cost landscape. So you can see that in each of these cases, people continue to walk at their original gait, which corresponds to a value of 0 on the y-axis. Now, if we go up to the center row, we can see the cost that corresponds with gait, and we can see that this is no longer the optimum in the new cost landscape. So this is what I mean by people do not spontaneously adapt. But like I mentioned earlier, people do eventually adapt after experiencing different costs in the new cost landscape. Particularly, people adapt after they experience a low cost. Sorry. Yeah, so people adapt after they experience a low cost. And this low cost, if you look in the center row, corresponds to a cost that's lower than the cost in the new landscape at their original gate. Okay, so people adapt after the experience with the low cost, but why does this experience initiate adaptation? To understand this, let's look at the right-hand side cost landscape. These are just illustrations. So once again, we have energetic cost on the y-axis and step frequency on the x-axis. The gray curve illustrates the original cost landscape, and the red curve is the new cost landscape. Now, this red dot in the new curve is the experience with low cost. And we can see that with this experience with low cost, the nervous system is able to detect salient cost savings. And this is important because it's only when the nervous system detects the salient cost savings that it knows that there's a change in the optimal gait. For example, I have another new cost landscape here that's given by the red dotted curve. So in the red dotted curve as well, the cost has changed at the original gate, but the optimum has not changed. And in the examples I gave earlier with the 3 different systems, it could have been that the curve either looked like this red dotted curve or this red solid curve. While we knew it was the red solid curve, the nervous system had to find out that the optimal gait has shifted. And adaptation is only beneficial when this optimal gait has changed. If the optimal gait has not changed, the nervous system is better off exploiting its previous prediction and staying at its original gait. So that's why experience with lower costs initiates adaptation. So then if we want to observe spontaneous initiation of adaptation, what we would like is for the nervous system to spontaneously detect salient cost savings. And like I mentioned before, during the spontaneous period, people are typically walking around their original gait, which is over here, which means they can only detect salient cost savings using their natural variability. So then one way to increase salient cost savings spontaneously is to increase the cost gradient. So that's what we did in our experiment. We designed 3 cost landscapes of increasing gradients, and we asked the question, do people spontaneously initiate adaptation in response to steeper gradients? Now on the right side is a figure of the system that we used to create these cost landscapes. This is the same system I showed you earlier, but in a bit more detail. So people walked on a treadmill at a constant speed, and they wore inertial measurement units on their feet. Using these, we measured their step frequency and passed that value to a real-time controller, which calculated the force we wanted to apply to the people and sent that command to a series elastic actuator, which then applied the force to the hip belt that participants wore. Now we used forces because that is what manipulated the cost landscapes of the users. And a backward force meant a metabolic penalty, whereas a forward force meant a metabolic reward. Throughout this time, we also measured their actual force, and we also measured the metabolic energetic costs using respirometry. Now on the left-hand side are the cost landscapes that we wanted to create. So the y-axis is metabolic energetic cost, and the x-axis is normalized step frequency. And the yellow curve here labeled as shallow is the same as the curve I showed you earlier, where we did not observe spontaneous adaptation. Therefore, we created that curve, but we also created 2 more cost landscapes that were steeper, shown by the orange and red curves over here. Okay, now moving on to the protocol. So on the right-hand side, I have retained the cost landscape image for reference. On the left side, I'm going to build in the protocol. So participants came in and they walked on the treadmill at a fixed speed when 0 force was applied on them. And that's what is indicated by this white bar just above the x-axis. And the x-axis itself is time. During this baseline period, we measured the step frequency. And we used this step frequency to calculate a normalized step frequency given by this equation below. And that normalized step frequency will be the y-axis on the slide. So after the baseline protocol, we had the adaptation protocol. And there is a lot going on here. So first, participants walked on the treadmill. And if you focus on the bar just above the x-axis, you'll see a gray area and then a black area. I'll talk about this gray area later on. There is a force being applied during this gray area, but it's not with the controller on. Whereas in the black area is when participants actually experience the 3 different cost landscapes that's shown on the right. And this is where we estimated their spontaneous adaptation. And at the end of this protocol, we also held participants at a lower step frequency using an audio metronome. And on the right cost landscape plot, you can see the cost that corresponds with this step frequency. Finally, we had a cost mapping session where we measured participants' actual costs in the cost landscape, and you can see the points where we sampled on the right-hand side cost landscape plot. Importantly, we always had this at the very end so that participants were naive during their adaptation protocol. Okay, so moving on to results. These are the first set of results. And what you're seeing right now is just the desired cost landscape. So on the y-axis is metabolic energetic cost, and on the x-axis is step frequency. And these are the desired cost landscape that you saw earlier, but just zoomed in a little bit. And on the right-hand side is a table with the same landscapes, but in table format. And here are the data. These are averaged across all participants. And we see that participants indeed experienced cost landscapes of increasing gradients. Okay, next we moved on to analyzing the adaptation data, and we found something interesting. We saw that participants shifted the step frequency prior to the new cost landscapes. So what do I mean by this? Let's look at the first left-hand side. This is once again the time series. So x-axis is time, y-axis is step frequency, but now we'll focus on this gray box area that I mentioned earlier. So this gray part is before the controller comes on and participants are not in the new cost landscape. And what's happening here is, if you look at the cost landscape figure, you can see the 3 new desired cost landscape, but now there is also this gray curve that I refer to as the original landscape. Now these are data from literature. I've used them just for illustration purposes here. And when participants start walking on the treadmill, they are typically at the originally preferred step frequency, which is around here. And you can see that the cost in all the new landscapes at this frequency is higher than the cost in the original landscape, which means that participants will feel a backward force when walking at the step frequency. Now, we didn't want participants to feel a perturbing force as soon as the controller comes on. So we spent the first 2 minutes slowly ramping up the force to match the force they will experience in the new landscapes. So that's what's happening during this gray area. Now we've done this before in prior experiments and did not see any shift in step frequency. But for some reason in this experiment, we saw that participants had a shift to a lower step frequency. We don't know why this happened, but given this shift, we compared all further spontaneous adaptations to the shifted step frequency, and we found that participants did not spontaneously initiate adaptation. Now on the left-hand side, I filled in data from a single representative participant, and on the right-hand side, you see dot whisker plots, where each color corresponds to the adaptation from a single participant. Finally, we measured adaptation after experiencing a low cost, and we saw that participants did adapt, just like we've seen in prior experiments. So that was the experiment, and here's just a quick recap and summary. In this experiment, we asked, do people spontaneously initiate adaptation in response to steeper gradients? We tested this by creating 3 cost gradients using fore-aft forces at the hip. We found that there was no spontaneous adaptation in any gradient, but participants do adapt after experiencing low cost, which is in accordance with previous findings. With that, we conclude that people do not spontaneously initiate adaptation simply in response to steeper gradients. Finally, I just have some discussion and thoughts about why we may not have seen adaptation in our experiment. One idea is that perhaps the physiological sensors for metabolic cost need a long, steady state, low cost experience, which they can get when we hold them at a lower cost using a metronome, but they're not able to get from the step-to-step sensing of cost that comes from gradient. Another explanation might be that the natural variability is not sufficient for the nervous system to determine which aspect of gait to adapt. While we only manipulated the cost landscape as a function of step frequency, it's possible that the nervous system was unable to detect this. Okay, with that, I just want to thank everybody who helped with this presentation, with this work, and the funding sources. And I'm happy to take questions.
Thank you, Surari. I think the first question that we have actually aligns with one of your discussion points being, what is your current thinking on how the nervous system measures metabolic cost?
How the nervous system, okay. We don't know how the nervous system measures metabolic cost. I guess there's been some work that's been done. Oh, maybe it's right here. Let's see. So these are some ideas. This was work done by Jeremy Wong, where they tested whether metabolic cost could be sensed by blood gas sensors, and they found that that is not the case. So these are some other options for measuring metabolic cost. But in these cases, it would mean that it's maybe a slow integrative process. And I guess that's why it was one of my discussion points, that if it is being slowly integrated, then perhaps the metabolic cost you sense from step to step could be lumped into noise, at least for what in the experiments that we did. Does that answer the question?
Okay, well, I'm gonna ask James Finley, who's raising his hand, to go next.
Hi, Surbi. Can you hear me okay?
Yes. Hi, James.
Yeah, so I was wondering, one of your finding here has to do, may have something to do with the steepness of the gradient as it relates to their natural variability. And so I'm wondering what you would think would happen if the gradient was steep enough such that within their natural variability, they experienced, let's say, an effort that was as low as what was experienced in the bottom figure you have in the middle column here. In other words, that yes, that they, there was just a much steeper gradient. Do you think that at some point people would learn to naturally initiate if the gradient was steep enough?
Yeah, so I think that's what we tried to address in this. So we went as steep as we could, which is the one we call steep here. We went as steep as we could without participants feeling perturbed. So in this gradient, when we just asked people later, they couldn't really tell that there was a force that was changing. And that was what we were going for, so that we wanted to make sure it's metabolic cost that we're really targeting and not some stability or some fear or something that affects them. So I guess based on these results, I want to say just increasing the gradient may not be sufficient for people to spontaneously initiate adaptation. There could be other aspects so one of the explanations I had was about just using the natural variability to determine how to adapt. And I actually, so in the variability you have, so this whole thing was based on the reinforcement learning framework, which we've spoken a bit about. And I guess part of that is your variability could be the nervous system, you intending the variability and trying to learn from it, as opposed, or just variability that's not useful. So it could be that here we're not targeting variability that the nervous system is using. And so even though we're steepening the gradient, the nervous system is not able to learn from it using its natural variability. That's my thought. But yeah, if you could find a way to make it really steep. This is pretty steep. So they can get about 10% to 20% reduction in cost. So that's a pretty steep gradient, I think.
Thanks, Ruby.
Okay, the next question is regarding retention. So do you know how long after experiencing low cost participants still show adaptation, and does the effect go away after a long time?
Ooh, I don't know how long. All of these were 5 minutes. I think they've gone I might have not these experiments, but in pilots had people go for 10 minutes and they still are around lower, but I don't think we've tested for very long really, because I think mostly we've measured between 5 and 10 minutes and then stopped the experiment after that. So I don't know. I assume they'll stay, if the cost landscape is the new landscape, I assume they've learned it and will stay there. Yeah.
Okay, and then one last question, and Andy, feel free to chime in. How quickly does the system respond to a person?
The force system, you mean? Like how quickly is the force applied?
Yeah, so you've got to measure the step frequency and then decide what force to apply. And
Yeah.
I'm nervous when I hear this, that it's a substantial time delay, and that it's just really hard for people to learn things that have time delays. I wonder if you have tried or considered some kind of experiment where something would respond more or less instantaneously to the person's behavior without, because you can, I don't know what you, when somebody changes the frequency, it probably takes 2 steps before you decided that they changed their frequency. And then you have to ramp up the force. So it must be at least 2-3 seconds, right? Delay there.
Yeah, so in this case, it's every step. So this is just a slide showing the force itself. Like this is without the person. If you command a force to the system, this is how long it takes to match the force. And in the experiment, we measure the step frequency at every step, and then that step goes to the controller, and we'll say for this step frequency, this is the force, and then you have this commanded force and then the applied force. So I would say it's within a step that they get the, so yeah.
So it's one step.
Yes, in this case, yes. We've tried other things where we filter it and it takes much longer.
Yeah. Okay. But so you, I mean, you don't, you don't think that the time delay is a significant part? Like if you had some, if you measured a knee velocity or something like that and gave feedback on that.
It's not that much time delay in how the force is applied, but maybe how things are sensed in the body is different, because there you're applying it on the knee as the leg is swinging, whereas over at different parts of the gait, whereas here it's applied really to the hip.
No, I was thinking apply force at the hip due to knee velocity to make it.
Oh, I see.
This is a great discussion. Surabhi, you have lots of questions on the chat, so
yeah.
You'll be busy for the rest
Yeah.
of today. Let's give Surabhi a round of applause. And our next speaker is Dr. Nidhi Sitapathy. She's currently a postdoc at Penn, and she will be starting her faculty position at MIT next year. So Nidhi will continue to talk about energetics, and she'll now bring balance into the picture.
Thanks, Natalie, for the introduction. So as Natalie mentioned, I'm going to talk about a theoretical framework that we've developed and are developing for locomotor learning. So I'm going to in detail talk about split belt treadmill walking within our framework that we've developed. And then I'll also comment on some predictions that our framework makes for sort of exoskeleton assistance towards the end, because I don't have enough time to go into the details of that as well. We've also worked on mass asymmetry. I won't be talking about that today. So split belt treadmill walking is the most popular sort of locomotor learning paradigm. This learning phenomenon has been examined over 35 years of studies through various experiments. And what the sort of theoretical framework we're proposing here is sort of a unified theoretical framework that can predict both the short and the slow time scale, short and the long time scale adaptations that happen on split belt walking. So let me tell you a bit about sort of the phenomenology of split belt learning. So what has been found is that, so you have a split belt treadmill where you have 2 belts going at different speeds, 1 foot on each belt. So one is a slower belt, other is a faster belt. And the sort of the paradigm that people study is that they have both belts going at the same speed for a certain time, and then they go into the split condition, and then they go back into the both speeds being equal again. And then they see how people adapt in this paradigm. And what they find are some stereotypical changes in both the step length symmetry and the step time symmetry. And this is so what they find is that when the belts are tied, there's a certain constant step length symmetry, and then there is a sudden negative step length symmetry. It goes towards 0, and then with more time it goes towards positive step length symmetry. I should call it step length asymmetry, sorry. It goes towards positive step length asymmetry, and then once both the belts are at the same speed again, you have this fast B adaptation. And similarly, you have some trends in the step time symmetry as well. And this sort of work has been established. Early work by Amy Bastian sort of stopped here, and then work from James Finley and later from Sanchez, Simha, and so on have shown that over a longer time scale, you have this positive asymmetry. So the question that we wanted to address with our modeling framework is, what principles underlie locomotor learning in a new environment. And sort of our hypotheses for this is that on a short time scale, the nervous system cares about and prioritizes stability. And on a long time scale, the nervous system cares about energy, while of course still maintaining stability. So stability is still important, but it's just that energy is sort of important on a slower time scale. So just to show you a schematic for how we go about modeling this, we have this sort of inner loop controller, a feedback controller, which is keeping track of the body states. And then there is some sort of initial feedback control that we derive from experiments. And the parameters of that feedback controller are in the outer loop on a slower time scale being changed by sort of a policy gradient reinforcement learner. So just to give a slightly more detail, so for the inner loop, we have some default control policy and sort of the tunable parameters. So U are the controls, U naught are sort of the feed forward control, K are the feedback gains, and S are the body states. S naught is sort of the desired body state. So you're keeping track of any deviations from the desired body state. And then the tunable parameters are the feed forward control, the gains, and the sort of desired state as well. And the outer loop, then what it does is it takes some measure of the energy gradient. I'll tell you how that gradient is measured in a bit, but let's ignore that for now. Let's just assume that it has some measure of the energy gradient. And alpha is sort of the learning rate. And what it does is it's tuning, it's just doing gradient descent and tuning these tunable parameters while adding exploratory noise on each step. And the reason we're adding exploratory noise on each step is to get more data points locally to be able to estimate the gradient better. And I think that the role of the exploratory noise will also become clearer in a minute when I talk about how that is really done. So, but let me first talk about how the initial controller, like how the initial control policy is chosen in our model. So the control policy looks like this, as I'd shown in the previous slide. The nominal parameters here, U naught and S naught, were derived from energy optimality. Basically, we did a trajectory optimization and we found what the model converges to at steady state, and we used those as sort of the nominal or desired. The initial feedback gain was derived from human data, from experiments, basically, and there are locomotion experiments done that sort of measure these feedback gains, and so we use those. And the initial controller here serves not just as an initial condition for what the person is going to do in this novel split belt condition, but it actually also serves as an inductive bias for subsequent learning, because the whatever further learning happens is shaped by the controller structure that we assume here. So so that's definitely something interesting to play with in the future also with this sort of modeling framework. Right now we've chosen this sort of controller framework, a controller structure, but one could experiment with other controller structures as well. And for now, the assumption here is that we're only modulating U naught and S naught and not really changing the gain itself by learning. So that's sort of the details of the controller for the model. And let me just show you a schematic for how the adaptation or learning happens in this framework. So you have some energy landscape for a normal treadmill, and you have some natural variability. You have a new energy landscape for a split belt treadmill. And then the person is estimating the gradients using the natural variability. And on each step, they're sort of moving as a combination of this sort of outer loop gradient descent and the exploratory sort of noise, they're moving towards the new energy landscape. And that's sort of the general schematic for it. So just to give you some details about how the gradient itself was estimated, we are basically assuming that on each step, the person is building a model of the dynamical sort of mapping between the past states and the current state, as well as the past controller parameters. And similarly, building a model between the current energy cost and the past states and the past controller parameters. And this is this is why we need the exploratory noise, because there are many parameters like A, B, C, F, G, H here that are trying to be sort of fit to this to find this model. And for that, you need many data points, which is why we hypothesize that people do the outer loop over many steps, because they will need many data points to be able to estimate the energy and hence the gradient. So specifically, the assumption that we're making here is that people are estimating the energy gradient sort of 30 steps into the future and performing gradient descent on that gradient. That is, sort of they're trying to estimate what the steady state gradient would be and doing gradient descent on that. And for that, they need like a certain history, and which is why they need like some sort of greater, longer time scale to do the outer loop, to do the gradient estimation. And so with this model, we're able to make some predictions for the split belt condition. And what we were able to capture sort of qualitatively all the behaviors that we find in experiments. So basically, we have the fast negative step length asymmetry, and then it goes towards 0, and then it becomes positive. And then once the person is again in the tight condition, there's some de-adaptation. Of course, there are some details that are not matching the experiment here because it's a very simple model. But one particular detail that I like to comment on, which I think is really interesting, is sort of we chose the same learning rate for both the adaptation and the de-adaptation. But as you can see in experiments, it seems like people actually de-adapt faster than they do adapt. And I think that's really interesting and can be modeled by incorporating something like memory, basically where, because of the sort of the tight belt condition is something that the person is much more familiar with. So it makes sense that they would maybe learn faster in that environment because it's a more familiar environment. So there may be this sort of familiarity or memory driven aspect, which is speeding up learning in sort of the tight belt condition. And that's something that I want to look into more going forward. And then we also, this is just the sort of metabolic rate predictions, which qualitatively match what have been found in experiments. I think the sort of what happens after the tight condition, the transient that happens in the metabolics after the in the sort of tight, in the de-adaptation phase, I'm not sure if that is really clear in the literature yet, so that it may be interesting to do some more experiments to sort of really understand that better. So there are these two pieces to the model that I've described so far. There's this inner fast time scale sort of controller, and then this outer loop driven by energy that is sort of a reinforcement learner. So let's tease them apart a little bit, and see what would happen if we only were driven by control or by like the controller, or if we were only driven by energy. So if we have only the controller without the sort of outer loop learning, what we find is we capture the fast initial transient. So it's sufficient to explain the fast initial transient. This looks like it's happening in 0 steps, but it's actually like 3 or 4 steps in this fast transient. And so, but it's not, of course, able to capture the slow transient or any of the de-adaptation. On the other hand, if we only try to predict, pure energy optimization, we'd of course need to sort of make some assumptions about periodicity. So implicitly, we'll be forcing the person to be stable by asking them to be periodic and to be able to do the task. In that case, in past work, we've shown that, pure sort of trajectory optimization with periodicity constraints can predict the positive step length asymmetry that people converge to after a lot of adaptation. But of course, this sort of modeling framework, unlike the sort of reinforcement learning framework or adaptive control framework, doesn't have the ability to predict the fast time scale transient. It only predicts the steady state because you have to assume periodicity. So I just want to now, play around with some of the parameters in the model and show you, what sort of different, what happens when we modify various things. So let's add in some sensory noise, keeping the exploratory noise fixed. So the way that we do this is we're basically adding noise in the gradient estimates. And so with very low sensory noise, everything proceeds as expected and it's all good. And then with medium sensory noise, you see that the learning is degraded a little bit. And then with large sensory noise, it actually, the learning completely goes away. So this is sort of one potential hypothesis for, why some people may not be able to adapt in a given sort of paradigm is if they have some sort of noisy feedback for whatever reason, relative, and note that this is always relative to the exploratory noise. So you can compensate for it by just increasing the exploratory noise. But there's also effects of modulating the exploratory noise too much. So if it of course, as I said, needs to be large enough to overcome the sensory noise. But if you, as you increase the exploratory noise, you will end up using more energy at steady state. So yeah, steady state energy consumption will be higher. So there is that sort of dissuasion to increase the exploratory noise for a person. Large exploratory noise also means greater gait unsteadiness. So you will be more likely to fall down. And of course, if it's very large, the biped will fall. And so we've sort of fixed the exploratory noise here, but there are some other ways to model the exploratory noise that can be explored in the future. We can make the noise different in different directions, and this could be inspired by actual sort of measurements for what people are doing and seeing if the noise is actually different in different directions and incorporate that into the model. And that may have some unique effects on the learning that predict when people do adapt and when they don't adapt. We could also make the size of the noise dependent on the internal model prediction error. That seems like somewhat of a sort of normative, meaningful thing to do, which is, explore more when you know that your sort of forward predictive model is making mistakes, then you want to explore more to improve the forward predictive model. And one can test if this is something that people do, or one can incorporate this into the model as well. Finally, I want to comment also on the different timescales that are in the model. And this sort of links back to something that Andy was commenting on during Surbhi's talk about, having enough time to sort of estimate the gradients. And Surbhi also mentioned it herself. So, so there are different timescales in our model. In the very fast timescale, there's the stabilizing control policy and the body dynamics. They sort of dictate the very fast timescale, and that's about happening on the timescale of 2 to 5 steps. And that was chosen in our model from human data, like basically from our human sort of data-driven controller inference work. There's a medium timescale on which the gradient estimation is happening, which I described earlier. So we've chosen specifically 30 steps here, but it's on the order of 10 steps. And then there's the very slow time scale of learning, where the learning control policy changes, and that's on the order of many hundreds of steps. And it is important for these timescales to go in this direction. And there is, therefore, there may be like a lower limit on each of these. Like the lower limit for the slow timescale would be set by sort of the gradient estimation, and the gradient estimation would be set by sort of the dynamics and the controller timescale itself. And these are all things that would be very interesting to sort of understand better empirically by particularly perturbing and trying to tease out these timescales. So as I had mentioned earlier on, we've used the same framework to capture other kinds of locomotor adaptation. I'll just quickly talk about our predictions using the same framework for walking with exoskeleton assistance. I'll talk about time periodic and phase dependent assistance. So there were these experiments done by Ochoa et al. And Ahn and Hogan, where they had this external time periodic assistance provided by an exoskeleton. And so we've modeled that here by sort of forward pulls at certain fixed time periods, and which is equivalent to having like an ankle push off for the model. And what they found experimentally is that people entrained to, they had some natural period, and then with the enforcing exoskeleton, they entrained to the period of the exoskeleton. And that is what the model sort of naturally shows as well. And we also wanted to do this for phase-dependent assistance, because phase-dependent assistance is much more common in the kinds of exoskeletons, robotic exoskeletons that people work on. People don't use sort of time-based controllers, they use phase-based controllers. And we show that it makes some predictions for that as well. So it would be interesting to do in the future an experiment that has sort of these forward pulls at regular sort of phases, and see if it matches what we predict here, where intuitively it sort of makes sense, where we have the step length at steady state is lower than the initial step length, which is kind of what people see when people walk downhill. And having this sort of phase periodic forward assistance is kind of like walking downhill.
Amity, you have 1 more minute.
Yeah, I think I'm basically done. So that's
perfect. Excellent.
Thanks a lot. And I didn't have summary slides, so hopefully you remember enough from the talk to ask me questions.
Thank you. I'm going to start with a question because I'm very curious about this idea of non-adapters, because we have definitely seen people that don't adapt experimentally. And I wonder if you can speculate if this non-adaptation is from that fast time scale that they never find a pattern that maintains balance, or from that slower component where they can't find like a reduction in energetic cost.
Right. So that's a good question. I think it will be hard to tease that out, without further experiments. The model, makes certain assumptions about how the gradients are estimated. And I think that's kind of where all the keys lie, like how the gradient is estimated. And I don't mean like biologically how it's estimated. Of course, that's an interesting question too, but even behaviorally trying to, get or rather empirically trying to understand, by doing different sort of perturbations and cases for these different adaptation tasks, we can try to infer how actually the gradient estimation proceeds. And I think that will help us infer, like sort of in an empirical way, what the learning rate is for a given person, or sort of what inputs and outputs, like what structure of the sort of state-to-state maps best predict the how the adaptation proceeds in these various conditions. But broadly, the model has a few pieces that can talk about when people don't adapt, right? One is what I spoke about, which is the sensory noise relative to the exploratory noise. Another potential explanation is the fact that the time scale, like for example in Surbhi's case, as she herself mentioned, our model would predict that the fast time scale, that if the exoskeleton is has a certain delay associated with it that the person has not incorporated into their own model for estimating the energy gradient, it wouldn't be able to estimate the gradient appropriately, right? So basically what we need to do in Surbhi's sort of framework is enable the person to realize that there's a delay and incorporate that delay into their gradient estimation. And it would be interesting to see if and how we can do that.
Excellent, great. There's a great question by James Finley in the chat. We're gonna wrap up. Thank you so much, Nidhi, for a great talk, and I look forward to seeing future results.
Thanks.
And our final speaker is Dr. Jason Franz. He is an associate professor in biomedical engineering at UNC and NC State, and he's actually going to integrate all this idea of energetics and balance into human studies. So take it away, Jason.
All right, and you can hear me okay, and my screen is shared? Perfect. So last, but hopefully not the least, thanks for the introduction, and good afternoon, at least here from the Eastern US. Let me thank the organizers first for the invitation and the other speakers for the really exciting talks. I've been sitting here learning so much already this afternoon. And now as the last speaker here, I'd like to close today's session by talking about something that I think a lot of us have a vested interest in, and that is the interplay between neuromechanics, economy, and stability of locomotion, whether we're biomechanists or roboticists. And because we have this wonderful opportunity to learn much more by moving beyond observational studies of usual steady state locomotion, I'm going to describe how these factors play out in the face of dynamic balance challenges. And in the spirit of this episode, in dynamic walking more generally, I'd like to focus on two task objectives in locomotion that I think have broad impact in human walking as well as Lego robotics. First, regulating push-off intensity, because we have to get from point A to point B. And two, preserving lateral balance, because we have to do so without falling over. I've seen some questions already in the chat about this. And I want to define dynamic balance right off the top here pretty loosely, maybe as an experimental paradigm that directly manipulates these task objectives as we measure the emergent changes in the stability and economy of locomotion. We might be surprised to see things that wouldn't necessarily be considered a balance challenge actually turn out to be just that, or vice versa. So let's start here. Many individuals, whether it be due to age or gait pathology, suffer from insufficient push-off intensity during walking. And because a burst of ankle power during late stance is a very economical way to power walking, this change is thought by many to contribute to a decrease in walking economy, accelerating fatigue. There's another side of that coin. It was about 30 years ago now that David Winter suggested that this vigorous push-off, this burst of mechanical power during late stands may actually be destabilizing, and thus that a reduced push-off intensity we might see may serve to mitigate that instability. In other words, a clear trade-off between economy and stability. Let's go ahead and test that premise. Our lab uses real-time biofeedback, sometimes for rehabilitation, but mostly as an experimental tool to establish cause and effect relations relevant to the neuromechanics of movement. Let me give you an example. So here, while participants walk on an instrumented treadmill, let's go ahead and extract the peak anterior or propulsive peak of the ground reaction force as a measure of push-off intensity on a step-by-step basis, while subjects use biofeedback to target values 20 and 40% larger and smaller than preferred. And you see here in that plot on your right that subjects are pretty good at matching these target values in different trials. We'll then go ahead and record expired gases using indirect calorimetry and estimate group average changes in net metabolic power, which we can see here. So in the red data, pushing off the ground with more intensity costs you more metabolic energy. That's not surprising. However, an insufficient push-off, shown here in blue, is equally, if not more, expensive. So we have the first bit of evidence in support of this theory. More recently, in a follow-up study, we used musculoskeletal modeling and bioenergetic simulations to identify the reason why. We showed that with an insufficient ankle push-off, more active work must be performed by proximal and less economical leg muscles, particularly during early to mid stance, which you can see here in this figure. And this comes as a significant metabolic penalty. Well, what do you think? Maybe that's just the price we pay for improved stability. Unfortunately, the data we have, at least, shows the exact opposite. Here we say dynamic instability measured via short-term divergence exponents in different planes of movement, as well as the fully reconstructed three-dimensional state space in the lower right. And in all cases, an insufficient push-off is not only metabolically expensive, it's also really destabilizing, at least in our young adult cohorts of subjects. So when it comes to this first task objective, regulating push-off intensity, we have yet to find clear evidence of a trade-off, and instead find that a sufficient ankle push-off is critical for both the economy and stability of locomotion. And our outcomes to date suggest that the onset of a diminished push-off may independently contribute to instability and worse economy. And further, these changes might require slower walking speeds. In that case, the selection of a slower walking speed could actually normalize metabolic energy cost and stability, which speaks a bit to the time course of gait changes we might anticipate in older adults or people with gait pathology. Now let's move to our second task objective. When it comes to preserving lateral balance, I think many of us would agree that it makes sense that doing so in the face of dynamic balance challenges may come with a significant metabolic penalty. And there's at least evidence in the literature of that, whether it be Jesse Dean's early work on downhill walking or Sean O'Connor's work on the metabolic energy cost of step-to-step variability. I'd like to show you some of our own data in support of this premise, but I'm also going to try and convince you that this interplay and the cost function is governing it may be time dependent and subject to adaptation. So the way we're going to probe this interplay between the neuromechanics, stability, and economy here is through the use of continuous optical flow perturbations. So these are designed to elicit the visual perception of lateral instability. And we've used these in many studies, and we know for a fact that they do a really good job at disrupting lateral stability. But for the study I'm going to focus on today, participants are going to walk on a treadmill for a total of 20 minutes. The perturbations are going to turn on at the end of minute 5, and they're going to turn off at the end of minute 15. And here, we're going to interpret foot placement kinematics in the context of stability. And again, indirect calorimetry is going to provide that measure of net metabolic power as our economy outcome. I'm going to leave our experimental protocol up for you on the left. And these panels on your right show step width, step length, and the respective variabilities during unperturbed walking. So the onset of perturbations, participants instinctively adopted what we've seen now in several studies, a generalized anticipatory strategy of shorter, wider steps to accompany the significant variability introduced by the perturbations. What we had here is that you're actually going to pay a 12% metabolic tax to preserve that lateral instability at the onset of these perturbations. However, and to use a word that Dr. Seema used earlier, over the course of 10 minutes, participants spontaneously abandon or at least deprioritize that generalized anticipatory control in favor of a more task-specific reactive strategy in which step-to-step corrections are made without the need for wider and shorter steps. Now, what's really interesting here is that this change in strategy used to accommodate the same exact magnitude of perturbations, it's actually going to improve walking economy by about 5%. So when it comes to preserving lateral instability, we found clear evidence for a trade-off between economy and stability in which the cost functions governing our underlying neuromechanics may be sensitive to changing task priorities. And this is some of the first evidence that we're aware of to suggest that metabolic energy costs may actually shape the strategies we use to accommodate balance challenges when we're walking in our communities. All right, so where do we go from here? Well, as one example, we're starting to dive deeper into the preferences that govern the selection of push-off intensity. We recently wrapped up this study here in which we used a nearly identical biofeedback paradigm with metabolic measurements, but we're going to do so using a self-paced treadmill controller in which subjects can instinctively modify their walking speed. You can very clearly see in this figure here the exploration in walking speed and the resultant average values after 5 minutes as people augment their push-off intensity using biofeedback. And ultimately here, we hope to better establish causal links underlying the selection of locomotor behavior. And then for the other side of this larger story, we've introduced a precision stepping paradigm using laser-guided targets projected onto the surface of a treadmill belt to explore the neuromechanical mechanisms underlying the clear trade-off we're seeing between walking economy and stability when working to preserve lateral balance. A laser and modifying foot placement to match that target. You can see that in the video here. It's a bit dark, but there's a target coming. And on the top, you can see some of our swing phase outcome measures that we use. Now in this work, we use electromyography to target the muscles most responsible for regulating lateral foot placement during walking. And for example, we've recently found that the gluteus medius dysfunction is a neuromechanical determinant of worse precision stepping ability during this task in older adults who are also subject to falls, subject to fatigue, and for which a trade-off might be quite relevant. And our obvious next step will be to include breath-by-breath measures and metabolic energy costs to our future studies. All right, so let me conclude here with just a few take-home messages about the interplay between the neuromechanics, economy, and stability of human walking. That interplay does appear to be task-dependent, with no evidence of a trade-off between stability and economy for ankle push-off. You essentially get both benefits or neither benefit. And then clear evidence of this trade-off between stability and economy for lateral balance. You will pay a metabolic tax to preserve stability. This interplay is also time-dependent and subject to adaptation. And if our biological control strategies are time-dependent, subject to adaptation, should those be for our exoskeletons or prostheses? Probably. And if that's the case, could or should those control schemes be designed to change the time course of adaptation or perhaps to steer it in different directions for different task objectives? Maybe. And then lastly here, given our personal interest in extending these discoveries to individuals with walking ability limitations or at risk of falls, we certainly expect to see the relative weightings placed on these individual factors change with age and disease, and it's a ongoing and future direction for our lab. So we have a really great group of folks from our lab presenting here coming up in the next month at ASB and ISB, but I'm going to emphasize the three you see here Ricky Pimentel, Shauna Huja, and Andy Shelton will talk in much more detail about the work that sort of contributed to my talk today. So I would definitely encourage you to check out their presentations if you can. And I'd like to acknowledge our funding sources for the study and thank you again to the dynamic walking organizers and the moderators and the other speakers. So I'd be happy to take any questions. Thanks.
Thank you so much, Jason. We have a question in the chat, and it's asking, when manipulating ankle push-off, this often manipulates step frequency. How do you ensure that the U-shape is because of ankle push-off and not due to changes in frequency?
Yeah, so what we have done, and this is something we've addressed in the limitations section of our papers, because these do change in the same direction. When you prescribe a reduction in push-off intensity, step frequency tends to go up. And when you do the opposite, step frequency tends to go down. But if you measure metabolics and you measure other biomechanical outcomes of people responding to prescribed changes in step frequency, and you plot those data as a U-shape. And then you plot the same sort of U-shape when subjects are responding to the biofeedback we prescribe, you get different U-shapes. And so that's at least some evidence to suggest that we've decoupled the changes in any outcome measure we tend to use for augmented push-off and augmented step frequency. But it is a difficult thing. I'll also comment that biofeedback requires the person pay attention, and you could imagine also adding a metronome in place. The tasks get really difficult if we do that as well. But I think that's the next step for sure.
Thank you. I also wanted to talk about this time component, and Nidhi and Surabhi can also contribute to this discussion, because I think it's very interesting whether these short duration tasks are kind of like the factors that are shaping behavior a truncated way of a long duration task, or are we just doing completely different things, right?
Mm-hmm. Yeah, and so we often use young adults as a model to manipulate their walking in order to make discoveries we hope to extend to, for example, older adults. And some of this interplay, we imagine older adults walking around their communities with diminished push-off, increased metabolic energy cost, increased instability and risk of falls, and an increased sort of fatigue state, increased fatigability. And so those preferences in selection and how they differ by age out in the community, I love some of the work that's being done with, even today, somebody mentioned, the sensor fusion, the wearable sensors getting out of the lab and looking at behaviors in the wild. I think that's the only way we're going to get at the bottom of this.
And I think, this aligns nicely with some of the work that James has done, Finley, just showing that, for example, in people after stroke, they just choose to not walk in a metabolically effective way. And I'm using the word choose here lightly, but because it does seem that there's other priorities such as balance, or the fact that they have impaired proprioception that doesn't allow them to rely on those sensors to maintain their balance. So they're sacrificing that.
Yeah, I fully agree. I see James is in attendance here. But the latest study where we're allowing people, we're prescribing the biomechanics and allowing walking speed to be an emergent outcome. We're learning a lot where there's mismatches between the biomechanics and metabolic energy cost you have when walking at a fixed speed and those walking at the same speed, but when you could get there on your own. And a lot of it, I'm having a hard time wrapping my head around, to be honest.
Okay, well, if there are no further questions, thank you, everyone. Thanks to all the speakers and to our audience. There was a great discussion.
I will add, so let me jump in here. First, thank all our speakers and our moderator, Dr. Sanchez. Thank you so much for keeping things running on time. I will add that, Jason, there were more questions in YouTube that I'm not fast enough on the copy paste trigger finger. So like they are definitely there, but there's plenty of opportunity for everyone to meet in the spatial chat, which I posted a link to, and we will reconvene for our short panel at 4 p.m. Okay, where we're thrilled to have Dr. Sentis, Daly, and Young-Hee Chang all together for a big chat about tasks and objectives. So I'll see you all on the spatial chat and see you back in the panel at 4 o'clock, and then the posters after that. Thank you, everyone. Hey there. All right. So everyone on YouTube, it's great seeing you. We'll be back. We will reconvene at 4 p.m.
Thanks, Christian. Really appreciate it.
My pleasure. My pleasure. Thank you. This is very exciting. I mean, there's so much that we plan in these talks, but all these emergent themes that keep coming out are also really interesting too. And I'm feeling that some of the talk points that you brought up may or may not make the panel session, whoever moderates that, So, all right. Fantastic. We will reconvene in approximately 15 minutes. Thank you all. We'll be going back live in just a few minutes while I pin up our new panel. All right. Great. Looks like we're all pinned up here. We'll get started in about 30 seconds while I lock my door so my dog doesn't come barging in. Just 1 second. All right. Okay. Now it's about time, I'd say, to get started. So anyway, thank you everyone for coming back for our panel, and especially a big thanks to our great panelists that we've invited to speak today. So thank you all for coming. Let me introduce everyone just in order here. First, I would like to introduce Dr. Monica Daly. She's an associate professor in the Department of Ecology and Evolutionary Biology at UC Irvine. Also, we have Young-Hee Chang, who is a professor of biological sciences at Georgia Institute of Technology, where he directs the Comparative Neuromechanics Laboratory, and Dr. Luis Sentis, thank you so much, and is associate professor in the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin, and the General Dynamics Endowed Faculty Fellow. I'm so excited to have you all here today. Thank you very much for coming.
Thank you, Christian.
My pleasure to have you.
Thank you, Christian.
So, all right. Well, let's get started here. So, a fair warning to my panelists. I'm going to go Young-Hee, Monica, Luis on this one, I think. Okay. So, my first question. All right. This is about tasks. This whole session is about tasks, and we saw some great talks. I mean, I remember we had Aaron. We had Aaron. He was talking about how tasks can be a bit discrete. So, how do we make human tasks? How do we break them up? But my question for you is, how do we determine the priorities for human and robot locomotion when we have so many tasks? And also, when do they switch? When should they switch, or should they switch at all? If they're should they not be discrete? So my question is about tasks and switching. So hopefully I buffered enough time for you, Young-Hee, to answer the question.
Yeah, I think it's a difficult question because trying to determine a task during something like locomotion, you're looking at an implicit task. You're not telling the people, or they're telling not their bodies what to do explicitly, other than maybe to go across the room. And so we have to look at in biological systems for clues as to what the control system might be cueing in on as a task in and of itself. So one thing that we've been doing over the past 10 years or so is to use movement variability as a way to peer into a window of the control system, and we can get ideas about what sort of control policies are at play. For example, in these experiments, we've used humans, cats, and rats to look at how the locomotor control is orchestrated across different hierarchical levels, like from joints to the limb, for example. And in all three species, we've seen that the joint dynamics are coordinated in such a way to stabilize whole limb dynamics. So whether we're talking about kinematics or kinetics, it seems to be a fairly robust finding, even across three different species. We also see it in different gaits, in before and after injury, from one step to the next, for example. So there we think we have some good ideas about what an implicit task priority might even be, or a task variable that's controlled. Now,
what I hear, I'm sorry to interrupt. I was just punctuating your point. It's almost not. It's almost that you can't get away from this idea of hierarchies. It seems a lot of the time when you talk about when people talk about tasks. I mean, that something's got to be at the high level, something's be at the low level. Am I paraphrasing you correctly? If you're talking joint level and stuff?
I think so. And at a low level, you're certainly regulating muscles, which are crossing and influencing how joints function. Of course, then the joints need to communicate with each other to then coordinate the limb function. And of course, if you have multiple limbs, then the limbs are coordinating
to control the whole body dynamics as well. So we've seen, for example, when you brought up the idea of switching a task, this is one of the beauties and frustrations of studying biological systems, is that they're really good at just doing whatever they want to do. They can switch tasks very quickly within a gait cycle. So if you took a person, for example, who's playing hopscotch, they might hop on one leg and then two legs and then back on one leg again. We've done a study on humans doing this, and we can see that they stabilize the single limb force under one leg using a very coordination and exploiting the redundancy of the joints within that one leg. And right by the time they take their next hop on two legs, they now are prioritizing the net force across both limbs rather than any single limb force. And they're able to do this, very smoothly without giving much thought to it, as any 10-year-old might do on a sidewalk. So yeah, it's interesting that switching can happen very rapidly. We know it happens and how quickly it happens. So it's an active area of study that we're trying to get at.
Well, let's move on to Dr. Daly here. So I want to hear how you view prioritization in the context of tasks and locomotion.
Okay, I'll be answering and kind of from an experimental, biologist perspective, similar to Young Hee. We try to design experiments that systematically manipulate the task demands by trying to change the mechanical demands and the risks associated with the task. So we've been thinking increasingly about, rather than priorities, we are thinking about risks of fatigue, risk of fall, risk of injury, and trying to design tasks where the animal then has to choose. And then increasingly, we want to leverage larger data sets to be able to look at how behavior changes from short time scales with repeated practice over longer time scales, so that we can start to get some information about the learning. But because these systems are so complex and the control hierarchies are both complex and not really very well characterized, I think it's really important that we try to combine experiments with model-based approaches, so that we have models that make falsifiable predictions based on hypothesized priorities. And so I think that it's really important to try to combine model-based frameworks with experimental frameworks to understand how humans and animals adjust their priorities over time.
So when you're talking about these model-based approaches, how detailed of a model are you talking about? Just like it's like, I mean, it spans a lot of different scales. I mean, you have some open sim wizards, I'm sure, in the audience, and you also have people who, like me, who just don't want to do anything more complex than Newton. So what's your take?
Well, I tend towards simple models, and I think that when we're talking about task level priorities, we're really talking about how the subject adjusts the overall mechanical energy, forces, and loading of the limb in order to meet the task level goals. And so I think that it is relevant to have a model that is abstracted at the whole organism level and work towards including feedback mechanisms at short time scales and longer time scales, so that you have sort of short-term reactive control to adjust to stabilize against perturbations, and long-term supervisory control to adapt speed and movement direction over longer time scales. But I think it's a big, important challenge to also try to bridge between these high-level models and more detailed musculoskeletal models, because they can reveal more information about what the risks actually are in terms of potential for musculoskeletal injury or muscle fatigue, and the trade-offs between potentially force, demands and economy and so on.
I can think of about 1,000 ways this transitions to you, Luis. Because as someone who has to who's worked with robots and exoskeletons on people, You know, I mean, I think about the fact that, you know, Monica talked about making sure that you don't, you know, hurt the person, you make sure you don't overload them. I know you deal with these whole body control mechanisms for exoskeletons all the time. So I'm curious about your perspective on tasks and how we switch between them with people.
Absolutely. So priorities arise naturally as a heuristic when you're controlling precisely these what we used to call redundant robots that can they can execute in maybe in a Cartesian space or in a floor space, multiple tracking tasks. And it's a way to sort of deal with a possible conflict between what motion planners come up with and what the feedback controllers can do. The motion planners, despite using either simple or very sophisticated models, they're always approximations. And by the time that you send those trajectories to the feedback controllers, they might not be able to be executed at runtime, and therefore you need a very quick mechanism. And priorities are a quick way to sort of decide what kind of tracking task you want to prioritize, either because of safety or because of other factors that are important to the maybe at the high level. We have observed that that feedback priorities, they are very helpful, in particular, as you were mentioning, in force augmentation, lower body exoskeletons, where there might be a conflict between tasks such as the force augmentation, the human force augmentation, maybe the gravity compensation and balance, especially when you are dealing with these exoskeletons that they have many passive degrees of freedom. And therefore, everything might not be able to be accomplished. And really, this is a very reactive technique because you don't really have a motion plan. You're just augmenting forces. And that have been tremendously helpful in order to maybe prioritize balance and not let the human fall with a heavy exoskeleton. But then for that particular instant in time, then give up on force augmentation for a few milliseconds. And the last comment I wanted to make regarding priorities is that these are, I'm talking here about feedback priorities, not sort of sequential task priorities, which is another field, another area. But they our experience that they play an important role on the stability of tracking tasks. And that is very underexplored. In one of the reasons because that maybe should not be explored in the time domain, should be explored more in the frequency domain, and that's difficult to do with high dimensional systems. But definitely the stability and the convergence of tasks, of feedback tasks, depending on the priority level, is an important observation, and it needs to be accounted for and maybe formalized in the control process as well.
There's so much to chew on there, Luis, and so maybe I'll use this to transition to maybe another topic, because I actually have gotten some great questions through our panelist system. So I won't hold you to any particular person has to answer these, but but Luis talked about stability, and I can't believe I didn't think of this question. So Steve Heim asked, and anyone can jump in on this: what's your favorite and least favorite quantification of stability, and why? So it depends on how hot of a take you want to give. Does anyone have a most or least favorite quantification of stability?
Well, I like the frequency domain stability criteria, gain margins and Nyquist criterion and so on and so forth. And unfortunately, many of them are not applicable to real robotic systems. And but we sometimes, even for whole body exoskeletons, we do approximate those systems as locally as linear systems, and then we apply those criteria. They are very powerful, and that would be my favorite at this moment.
So you would be one of the people that likes these sort of linearized versions or even frequency domain stability concepts that we might learn in System Dynamics 1 or something, is what I'm hearing.
Right, because those allows you very aggressive feedback behaviors, right? Very sort of real-time behaviors that they allow you to the design of like things like loop shaping filters, for instance, right? That they are very powerful for like, again, back to the force augmentation tasks. They are very aggressive. You wanna measure the sense, the interaction with a human, and then produce the most aggressive augmentation possible, and that really belongs to those areas rather than temporal criterions. But of course, there's many others that are as well applicable.
Well, I imagine we're going to hear about a few of those right now, because I'm sure there are some things that linearized stability metrics and frequency domain can't cover. So Younghee or Monica, do you have a thought on this classic question?
I think it's a really challenging question when you're studying human and animal locomotion, because we don't really know what animals and humans actually care about in terms of stability. And so you might say, I think a big picture metric for stability is just maybe probability of task completion. How many steps before you fall, or how likely are you to get to your destination? But that's not particularly useful in terms of a real-time control algorithm, perhaps. So that's maybe a problem. But we see, in fact, in our birds, individual variation in preferences. And when we have birds running on slippery terrain where we drastically increase the risk of fall, some of these birds immediately adopt a strategy where they slow down and take very careful steps to avoid slipping and falling. And so clearly some stride to stride measure of stability is relevant, but some of the birds just keep running forward and they fall down and they get back up. And so even just a stability metric related to falling isn't particularly relevant to that animal.
And I'm going to want to know from the humans, cats, and rats expert among us, that's a whole bunch of different kinds of leg or morphologies. Clearly, you must have some kind of idea of or thoughts about stability amongst all these different morphologies.
Yeah, it's a loaded term, and I try to avoid it as much as I can. I find them all sort of unsatisfying in one way or another. I think the simple "does the person fall over" is obviously understandable to everybody, but it doesn't give you much quantification. And then as you start to quantify more and more, all the way on a spectrum, you can get more computationally abstract from the actual organism. You can quantify it more, but then it seems to get away from sort of an intuitive sense for what is going on. So yeah, I mean, I've done it in the past in terms of a linearized system and trying to project variance structures on a task. I know others on the call and in the chat have done it different ways. So I think as long as you are very careful about defining how you're going to, what you mean by stability, and then you just sort of play by those rules, I think that's okay. But I don't really find any of them like wholly satisfying.
This sounds like a very let's all just get along kind of answer to stability questions, which is fine. But you're actually saying, but you're also saying, but on some level, it's unsatisfying to you, and which I think that you wouldn't be alone in that view. I mean, and one thing I want to point out about Luis's work is that, like, when I'm teaching students about these stability concepts in CISO systems, I think about, how relevant is that? But his work is actually showing, like, for a lot of these like muscle impedance tasks, it's really effective. So. So moving on, I think we're sort of two short topics I want to talk about here, but before we wrap up our short but impactful panel. So our next thing I want to ask about is a common theme of this conference, which was adaptation. Okay, and are seeing robots adapting faster to more tasks. We have people see quantifying animal locomotion for more tasks, animal adaptation for more tasks. I mean, but I want to hear, maybe starting with maybe Luis, like, how do we know that is what's fast enough adaptation for robots? And perhaps from Younghee and Monica, how do we even measure adaptation? Is time scales enough? So Luis, what's your thought?
Yeah, and I think here we have another term that it has been heavily used in the control theory communities, and more recently is being extended to sort of things like lateral learning or persistent task execution or things that are of a longer time horizons. But let's go first at the low level. Adaptation or adaptive control can be defined as a feedback parameter changing a strategy based on perceived changes. That could be, adapting gains and adapting other parameters. Priorities can be another form of adaptive feedback control strategy. And they are, what kind of metrics we can use. And, the typical one is maybe tracking errors. And as you, is there a way to perceive the changes on the mechanical systems and adapt the gains as you perform the real-time tasks. Moving on into sort of a longer horizons, I think the ML community, I like the measures of adaptation. One of them perhaps is task progress, right? As you, let's say you walk from point A to point B on a rough terrain, and then you perform, learning episodes and over in the orders of millions and billions. So that's a compelling measure of adaptation of how it adapts to the terrain as you learn more and more over the zillions of episodes that you are running from. And then one thing I wanted to also talk briefly is that there is also the area of lifelong learning. And that's continuous learning across experience, not only across experience over many tasks, but also and then really long-term horizons, but also across different machines, and the transfer of the sequences of the task, right? And a single particular task, how to learn across tasks and how to sequence and how to learn our robots, and that's also something worthwhile to explore for our communities, or what kind of metrics they use for adaptation and those sequencing of tasks.
So I'm going to be, thank you. And just to reinforce that point, I'll probably go to Young Hee next is what I think. But you're talking about short-term tracking errors, something controls theory people deal with a lot. Long-term, these plots I always see in the machine learning community of this thing that looks like this. Right, that's what I'm envisioning there. So Young Hee, what adaptation for you? I know you do split belt treadmill things. I've seen your lab.
Yeah, I think this is a topic that's very interesting to me. I think this has come up in earlier talks today as well, but the idea of timescales and something like split belt treadmill walking, you can adapt on the order of minutes, which is relatively fast. We've done work on animals where if you apply a surgically precise peripheral nerve injury, so you sort of are impacting one of the joints in particular, like the ankle joint, it might take a cat 3 weeks to adapt, to sort of recover the whole limb kinematics or the endpoint trajectory profiles that it had before the injury, despite the fact that the joint kinematics never come back to normal. And so, it's interesting, this idea of timescales. The way I think of it is that we have a multi-dimensional system like a leg. We have a null space that we can use to stabilize. I'll use that word. Stabilize something like endpoint position. And then adaptation is really where you live in that null space and what external factors are sort of pushing you in what direction within that null space. That's one way to think of it. Because at least in the examples that I've talked about, you're still able to achieve these tasks, like an endpoint position task, despite the fact that the elements that make up the limb segments are doing something very different in each case.
A lot of thoughts on that, but I think I'll have to move on to Monica to get her thoughts on adaptation here.
I want to avoid covering what's already been covered here. So I think I'll just add that when we're trying to understand adaptation on short and long timescales, I think it's really important for us to embrace and understand individual variation. Many historic studies of, biomechanics and locomotion really try to kind of look at the group average response and treat individual variation as a random effect. But when we're talking about adaptation, every individual has a different starting point based on their experience, their musculoskeletal capacities, and their prior risk of exposure related to the task. And then, so I think it's really important to measure these things over long timescales and then within individual within an individual to look at how they adapt and change over time.
That's an interesting point. This is a great array of points we're getting here. We're not going to get enough time to go through all the topics I imagine I've seen people talk about in the in the chat, like the Atkinson Index. I'm a big fan of that as well. But so I put out, in order to finish up our short panel discussion, and maybe we'll go in reverse order of where we started here. So we'll start with Luis, then Monica, then Young Hee. I want to, we have a lot of early career people in the audience who probably want to know what they should be researching. And I think they want to a lot of them want to hear what the next big thing is from your perspective. Like if you're maybe it's a project you're working on right now, but what's the next big thing in this subtopic? So let's start with you, Luis.
Well, I think bringing the human in the loop as a teammate. I mean, exoskeletons obviously naturally have it, but beyond exploring tasks that are sort of very interactions are sort of very physical in nature. Exploring other areas in here talking about priorities and objectives. I'm a fan of, for instance, exploring what I call psychophysiological sensing, which are variables using brain imaging and bringing sort of preferences and perhaps even simpler metrics, trust and workload, which are things that can be measured. And then based on those, if there is a close interaction between the physical system and the robot or the exoskeleton, for instance, change the behavior based on what we believe the human is thinking, right? If a human is wearing an exoskeleton and the exoskeleton is about to change a decision, maybe the exoskeleton has a camera, is able to see scaffolding, is able to see that the human is going to fall on the scaffolding, and is able to apply a correction, but only applies the correction if there is a brain imaging sensor that tells that the human trusts the exoskeleton or something like that. That's one of the areas that I like. And the second one is that humans, when they do like very aggressive sports, let's say human soccer or basketball games, they are willing to take incredible risks. They're able to break a leg if they are in the Euro final, like we had last week, right? And there's a final in the final 5 minutes, and they're going to score a goal, and that is going to make their country and their team win. They're really willing to break a leg, right? So the priorities clearly change depending on what is at stake. So understanding these sort of other dimensions beyond that instantaneous rewards is also very important.
Well, that's really interesting. I mean, and I think you're definitely in good company with some of the talks we had today. We heard Aaron Young talking about environmental parameter regressors. That was the term he used, which is interfacing with different kinds of human sensing. But yeah, I'll leave it to the professional soccer players to break their legs. I'll leave mine fine. So Monica, what's your next big thing?
I think the next big thing, or an area that I think is particularly exciting, is really trying to move from the lab out into the real world with biomechanics. So this is a growing area where we have sensors that are really powerful to measure lots of things on individuals over long time scales, moving out in the real world about their daily lives. And so I think that's a really exciting area. And we really want to push to take some of the fundamental principles that we've learned through dynamic walking and try to apply those in the context of interactions in the real world, and then leveraging some of these big data techniques to get insights on adaptation over short and long term timescales.
So when you're talking about real world, we're talking people in cities, talking ecology of animals?
Both of those things, right? People walking around cities, people going about their daily lives in their homes, trying to understand how people actually move in their daily lives, but also there's enormous scope for getting a better understanding of animal biomechanics and the diversity of animal form and function by trying to take biomechanics out into the field and using cameras and automated tracking technology to get a rich data set of how animals interact with their environments under different circumstances. So I think moving towards these large scale data sets and trying to use model-based approaches to get insights into those data sets is a big way forward.
Well, that leaves us with you, Young Hee. What's your next big thing?
I think one of the things we've been talking about today, task priorities, they really rely on abstract representations of some movement task. And because of that, we're really talking about the nervous system integrating literally thousands of different inputs and putting out probably as equally as many actuation control signals. And so how does that happen? So that's really what's got me interested in. How do you represent something? There's no single sensor, for example, for an endpoint force. If you're trying to control endpoint force on your foot or your finger, now there's no sensor for that. There's no single sensor for that. And there's no single actuator for that. So it really requires an abstract neural representation of this task. And so that's really, I think, an interesting area for the future. This idea that this takes me sort of above the brainstem, which I thought I'd never go, but how do you learn these representations? How do you adapt them? I think areas of cognitive neuroscience are going to become more important for people like myself who are typically just interested in how things move around and measuring, kinematics and things like that. So I think how do you represent some basic fundamental properties like gravity and how generalizable is it? I don't want to steal Chase Rock's thunder, who's I think in this meeting, but that's one of the questions we're tackling. I think that it was also brought up today. How do you sense very abstract whole body things like metabolic cost? And so we're tackling some ideas of what could be done there. I'd love to talk more with folks about that, but we think we have at least a few sensors in mind that it looks like we can sense metabolic costs on a fairly fast timescale.
Well, it sounds like we'll have plenty of opportunities for lots of discussion in the spatial chat right after this. So I'll post another link in the chat. But first off, so this takes us to the end of our panel, and it was short but oh so sweet. So I want to thank Luis, Monica, and Young Hee. Thank you so much for letting me ping questions off of you, from our chat. I hope, and if you're available, we'd love to have you in the spatial chat, the chat with our beloved participants. So thank you very much.
Thank you, Christian.
Thank you all. That's been great.
Thank you.
So this brings us to the end of our official talk section of this third episode of Dynamic Walking, and thus also the end of our 2021 virtual dynamic walking series as run by me and Greg Sawicki. So hopefully Greg is in here still, and we can. I want to thank Greg for all as my partner in organization in making this conference possible. He approached me and said, "Hey, you want to do dynamic walking?" And I'm just like, "Sure, sounds great." And so and so much of this was his great vision. I thought he he came in with a strong vision of what he wanted to do for this meeting, and I was pleased that I could help him out. I also want to thank his three of his researchers, Jenny Liestma, who, if you like the website, thank her. She did a wonderful job. Owen Beck has been on top of the promotion, Dr. Owen Beck. So thank making sure everyone knew about what was going on and handling the spatial chat. Also, this beautiful dynamic walking art that we have not sold in the form of official paraphernalia. That's Lindsay Trejo, one of Greg's students, made all that. She's got a future in both science and graphic design. So thank you to her. I also want to thank two of my students, Tienza Wang and Jacob Hackett, who made a lot of the behind the scenes emails and things work and putting up all the things on the website. So thank you to Tienza and Jacob. So for now, we will now retire to the spatial chat. I will put that in the chat for everyone to see. And thank you all for coming and making this a great series of conferences. So awesome. Talk to you all soon in the spatial chat. You have a wonderful day. Will there be a number 4? Let's see here.